There is a ring in space 1.3 billion light-years wide, and it should not be there. This thing is 3 times larger than anything physics allows to exist, and it is not alone. Just next to it, in the same patch of sky, there is a wall of galaxies stretching 3 billion light-years from end to end. 2 impossible structures, side by side, both confirmed, both real, both quietly erasing the rules we thought governed reality at the largest scales. The James Webb Space Telescope did not set out to break cosmology. It was built to answer questions, to fill in gaps, to refine what we already knew about the early universe. Instead, it has spent the last 2 years handing us objects that do not fit. Galaxies that formed too fast. Stars that ignited too early. Structures too massive, too organized, too vast to have assembled in the time available since the Big Bang. And now this, the Big Ring, the giant arc. Objects so large they violate something called the cosmological principle. The assumption that at the biggest scales the universe should look smooth, uniform, predictable. Except it does not. It never did. Scientists have a word for the maximum size a cosmic structure can reach before the universe runs out of time to build it. 1.2 billion light-years, that is the limit, the ceiling, the line nothing should cross. The Big Ring is bigger. The giant arc is nearly 3 times bigger, and no one can tell you how they got there. This is not a story about what we have discovered. This is a story about what we thought we understood and how close we are to admitting we were wrong. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. The James Webb Space Telescope was not supposed to break anything. It was supposed to answer questions. Specifically, it was supposed to answer questions about the early universe that Hubble had been circling around for 30 years without quite being able to resolve. Where did the first galaxies come from? How fast did they assemble? What did the universe look like in its childhood, back when it was still figuring out how gravity worked and stars were just beginning to light up the dark? These were good questions, important questions, the kind of questions you build a $10 billion telescope to answer. NASA launched Webb on Christmas Day 2021, folded up inside the nose cone of an Ariane 5 rocket like the most expensive piece of origami ever constructed. It traveled for a month to a gravitationally stable point about 1.5 million kilometers from Earth, unfolded its enormous gold-plated mirror segment by segment, and began the slow, meticulous process of cooling down and calibrating its instruments. By mid-2022, it was ready. The science team released the first deep-field image in July. President Biden unveiled it at a White House event. The image showed a patch of sky so small you could cover it with a grain of sand held at arm's length. Within that patch, Webb had captured thousands of galaxies, some of them so distant that their light had been traveling toward us for more than 13 billion years. The reaction was exactly what you'd expect. Awe, wonder, a collective sense that humanity had just been handed a new set of eyes, and then, very quickly, confusion. Because almost as soon as the telescope was switched on, astronomers started seeing things that didn't belong. Not small things, not subtle deviations buried in the noise. Big, bright galaxies everywhere in the early universe. Galaxies that, according to every model cosmologists had spent decades refining, should not have existed yet. Galaxies that were too massive, too well organized, too bright for an infant cosmos that was supposed to still be stumbling through its awkward phase. Let's back up for a second and talk about what makes Webb different. Because this isn't just a bigger Hubble, it's a fundamentally different kind of instrument. Hubble sees visible light and a bit of ultraviolet. It's essentially a very expensive version of what your eyes do, just vastly more sensitive and parked above the atmosphere where Earth's air doesn't blur the view. Webb, on the other hand, sees infrared, heat, the kind of light that gets emitted by objects that are either very cold or very far away. When a galaxy is sitting 13 billion light-years from Earth, its light has been stretched by the expansion of space itself. The ultraviolet and visible wavelengths that left the galaxy billions of years ago arrive at our telescopes as infrared, shifted so far toward the red end of the spectrum that Hubble can barely detect them. Webb was built specifically to catch that stretched light. Its primary mirror is 6.5 meters across, more than 2.5 times the diameter of Hubble's. It's made of 18 hexagonal segments, each coated in a microscopically thin layer of gold, because gold reflects infrared better than almost anything else. The entire structure had to be folded to fit inside the rocket, then deployed in space with a precision measured in nanometers. If any one of the 144 actuators controlling the mirror segments had failed, the whole mission would have been over. None of them failed. The mirror unfolded, aligned itself, and began collecting light with a sensitivity that made Hubble look like a pair of reading glasses. The other thing Webb has is patience. It orbits the Sun, not the Earth, which means it doesn't pass through Earth's shadow every 90 minutes like Hubble does. It can stare at a single patch of sky for hours, days, weeks if necessary, accumulating photons one at a time from objects so faint that no previous telescope would have registered them at all. That combination of infrared sensitivity, mirror size, and uninterrupted observation time is what allows Webb to see galaxies from the first few 100 million years after the Big Bang. Hubble could glimpse hints of them. Webb can study them in detail. The first surprise came from a dataset released in the summer of 2022, just weeks after Webb's science operations began. A team analyzing the images found 6 candidate galaxies that appeared to have formed between 500 and 700 million years after the Big Bang. That timeline alone was startling. 500 million years sounds like a long time until you remember that the universe is nearly 14 billion years old. In cosmic terms, 500 million years is infancy. It's the geological equivalent of finding a fully developed human skeleton in a layer of rock that predates multicellular life. What made these galaxies genuinely shocking wasn't just their age, it was their size. Some of them appeared to rival the Milky Way in mass. Our own galaxy took more than 13 billion years to assemble itself into its current form, accreting gas and smaller galaxies piece by piece, building up its spiral arms and central bulge through countless mergers and slow gravitational collapse. These 6 objects, if the measurements held, had done something similar in 1/10 of the time. One researcher described them as universe breakers, not because they literally broke the universe, but because they broke the models. If these galaxies were real, if the mass estimates were accurate, then nearly every atom of gas in their surrounding regions would have had to collapse into stars. The standard efficiency for star formation in the early universe sits around 10%. 90% of the available material just drifts, gets blown away by radiation, or stays too hot to collapse. These galaxies seem to be running at close to 100% efficiency. That doesn't happen, or at least it's not supposed to. The reaction from the broader astronomy community was a mix of excitement and deep skepticism. Some scientists started running the numbers immediately, trying to figure out what kind of physics you would need to build galaxies that fast. Others looked at the data more carefully and started poking holes. Redshift estimates, the method used to calculate how far away and how old a galaxy is, can be tricky. If you misidentify a spectral line, you can place an object much further back in time than it actually is. Dust can also fool you. Dust inside a galaxy absorbs blue light and re-emits it as infrared, which can make a closer, dustier galaxy look like a distant, intrinsically bright one. The 6 candidate galaxies hadn't been spectroscopically confirmed yet. They were photometric estimates, meaning the distances were educated guesses based on the colors of light Webb detected, not precise measurements from a spectrograph. Follow-up observations were scheduled. Some of the candidates were confirmed, others were revised downward, their distances shrinking, their ages becoming less impossible. A few turned out to be something else entirely. Compact systems dominated not by stars but by actively feeding black holes, objects that came to be nicknamed little red dots in later analyses, not galaxies in the traditional sense. Something weirder. The universe breaker label started to feel premature, but the underlying tension didn't go away. Even after the most extreme candidates were walked back, Webb was still finding more massive galaxies in the early universe than the standard model comfortably predicted. Another early shock came from an object called JWST 13-1. The name is a mouthful. JWST stands for the JWST Advanced Deep Extragalactic Survey, one of the major observation programs designed to push Webb to its limits. This particular galaxy was seen as it existed about 330 million years after the Big Bang. That alone would have been noteworthy. What made it stranger was the detection of a strong Lyman alpha emission line in its spectrum. Lyman alpha is a specific wavelength of ultraviolet light emitted by hydrogen, and it's one of the most common signatures astronomers use to identify distant galaxies. The problem is that the early universe was filled with neutral hydrogen gas, a cosmic fog that should have absorbed Lyman alpha photons before they could travel very far. Finding a strong Lyman alpha signal from a galaxy this early was unexpected. It suggested either that this particular galaxy had carved out a bubble of ionized space around itself much faster than models predicted, or that the surrounding intergalactic medium wasn't as opaque as everyone thought. The researchers running the JWST program were careful in their language. They noted the anomaly, they discussed possible explanations, they didn't claim to have overturned cosmology, but the data kept piling up. Every new deep field Webb observed seemed to contain more early galaxies than anticipated, not just 1 or 2 outliers, entire populations of them, and they weren't faint, struggling proto-galaxies barely holding themselves together. They were bright. They had structure. Some of them had disc-like shapes or signs of spiral arms, features that were supposed to take billions of years to develop. One of the strangest aspects of Webb's early findings was how quickly the public got involved. NASA and ESA, the European Space Agency, made much of Webb's data publicly available almost immediately after it was processed. That meant amateur astronomers, citizen scientists, and anyone with a decent computer and some image analysis software could download the raw files and start looking. Some of these amateur efforts were more successful than others. A few independent researchers flagged objects that professional teams had missed. Others made wild claims that didn't hold up under scrutiny. The result was a kind of chaotic, collaborative gold rush, with discoveries and retractions happening faster than the traditional peer review process could handle. Social media amplified everything. Every new Webb image got dissected in real time by thousands of people, many of whom had no formal training, but a lot of enthusiasm. That enthusiasm was both helpful and messy. It kept attention on the science. It also generated a lot of noise. Headlines started calling every unusual object Webb found a crisis for cosmology or a death blow to the Big Bang, which was frustrating for the scientists actually doing the work. The Big Bang wasn't in trouble, The broad framework of cosmic expansion, the cooling of the universe, the formation of the first elements, all of that was still on solid ground. What was in trouble were the details, the timeline, the assumptions about how quickly things could assemble in the early universe. Those details mattered enormously, but they weren't the kind of thing that fit neatly into a tweet. One particularly telling example of how messy the process got involved, an object called LIDE 568. Early observations suggested it was a black hole in the early universe feeding at 40 times the theoretical Eddington limit, the maximum rate at which a black hole should be able to consume matter without the radiation pressure from infalling gas blowing everything away. If true, that would have been extraordinary. It would have required new physics. Later analysis showed that the effect was almost certainly caused by dust surrounding the black hole, which scattered and amplified the light in a way that made the feeding rate look much higher than it actually was. Not super Eddington accretion, just dust doing what dust does. The initial claim was walked back quietly. But for a few weeks, it was treated as another impossible discovery, another piece of evidence that Webb was rewriting the rules. What made all of this so disorienting for astronomers wasn't that Webb found unexpected things. Unexpected things are the whole point of building new telescopes. It was the speed and volume of the surprises. Hubble had spent decades slowly refining our picture of the early universe. Webb showed up and immediately started poking holes in that picture. And the holes weren't random. They clustered around a specific set of problems. Galaxies forming too fast, black holes growing too large, structure appearing too early. Every observation seemed to push the timeline backward, compressing billions of years of expected evolution into a few 100 million. Part of what allowed Webb to see these objects at all was gravitational lensing. When light from a very distant galaxy passes near a massive foreground object, usually a galaxy cluster, the gravity of that cluster bends the light like a lens, magnifying the background galaxy and making it appear much brighter than it would otherwise. Webb's early deep fields deliberately targeted regions where massive clusters were doing this natural magnification. The result was that some of the faintest, most distant objects ever detected were being boosted into visibility by the universe's own optical equipment. Without lensing, many of these early galaxies would still be invisible, even to Webb. The downside is that lensing also complicates the analysis. You have to model the foreground cluster's mass distribution, figure out how much it's magnifying the background, and correct for distortions in the shape and brightness of the lensed galaxy. Get any of that wrong, and your distance or mass estimate can be off by a significant margin. One of the more memorable quotes from the early Webb era came from a researcher describing star clusters found inside a very early galaxy. The team saw a little chain of bright dots and called them cosmic gems. What struck them wasn't just that the clusters existed, but that they were so clearly defined. Individual clumps of stars resolved at a distance of more than 13 billion light-years. That kind of detail was impossible before Webb. Hubble would have seen the galaxy as a single fuzzy blob. Webb could pick apart its internal structure, identify regions where star formation was concentrated, and start asking questions about how those clusters formed and what they might tell us about the earliest stages of galaxy assembly. The strongest critical response to the early Webb findings wasn't outright dismissal, it was caution. Researchers kept emphasizing that the first results were preliminary. Redshifts needed spectroscopic confirmation. Mass estimates needed more careful modeling. Dust, selection effects, and instrumental quirks all had to be ruled out before anyone could confidently say that the standard model was in real trouble. But underneath that caution was a growing sense that something genuinely strange was happening. Too many independent observations were pointing in the same direction. Too many different teams were finding similar anomalies. The phrase that kept showing up in papers and conference talks was that the results challenge almost every model of the ancient universe. Not prove wrong, not overturn, challenge. Which in scientific language is about as close as you get to saying we don't know what's going on here without actually saying it. Webb was designed for exactly this kind of work. Its entire mission was to look back to the earliest moments of cosmic history and figure out how the first stars and galaxies came into being. The surprise wasn't that it found interesting things. The surprise was that the interesting things showed up immediately in the very first datasets before anyone had time to prepare for them. There's a difference between discovering something unexpected after years of careful observation and having the unexpected shoved in your face the moment you turn the telescope on. Webb did the latter. And once the initial shock wore off, astronomers had to start taking seriously the possibility that their picture of the early universe wasn't just incomplete, it might be wrong in some fundamental way. Which brings us to the question that was starting to form in the back of everyone's mind by the end of Webb's first year. If galaxies could grow this fast, this early, what else was out there that we hadn't seen yet? What other structures might be hiding in the data, waiting for someone to notice them? And if the universe could surprise us this much in its first few 100 million years, what might it have been doing on larger scales, over longer timescales, that we'd been missing all along? Those questions didn't stay hypothetical for long, because while Webb was busy finding impossible galaxies in the distant universe, another astronomer working with different data was about to find something even stranger. A structure so large, so organized, and so fundamentally at odds with the rules of cosmology that it would force physicists to confront a possibility they had been avoiding for nearly a century. The possibility that the universe at its largest scales does not behave the way it's supposed to. Those questions didn't stay hypothetical for long, because while Webb was busy finding impossible galaxies in the distant universe, another astronomer working with different data was about to find something even stranger. A structure so large, so organized, and so fundamentally at odds with the rules of cosmology that it would force physicists to confront a possibility they had been avoiding for nearly a century. The possibility that the universe, at its largest scales, does not behave the way it's supposed to. Her name is Alexia Lopez, and in early 2024 she was a doctoral student at the University of Central Lancashire in England. Lopez wasn't using Webb. She was working with data from the Sloan Digital Sky Survey, one of the longest-running and most comprehensive maps of the observable universe ever compiled. The Sloan survey doesn't take glamorous deep-field images like Webb does. It catalogues positions, distances, and spectra for millions of galaxies and quasars across enormous swaths of sky. It's a census, not a portrait. And buried in that census, Lopez found something that shouldn't exist. She called it the Big Ring. The name is almost comically straightforward. It's a ring. It's big. Specifically, it's a roughly circular arrangement of galaxies and galaxy clusters spanning about 1.3 billion light-years across. To put that in perspective, the Milky Way is about 100,000 light-years wide. The Big Ring is 13,000 times larger. If you shrank the Milky Way down to the size of a quarter, the Big Ring would stretch from New York to Los Angeles and back, twice. Lopez didn't find the structure by accident. She was specifically looking for large-scale patterns in the distribution of matter across the universe, using a technique that involves mapping something called magnesium-2 absorption systems. Magnesium-2 is a type of ionized magnesium that shows up as a distinctive signature in the spectra of quasars when their light passes through clouds of gas along the line of sight to Earth. By analyzing how many of these absorption features appear in quasar spectra at specific distances, astronomers can trace where gas and galaxies are concentrated in three-dimensional space. It's not a direct image. It's more like reconstructing the shape of a coastline by listening to where waves are breaking. The Big Ring showed up as a coherent, nearly circular overdensity of magnesium-2 systems sitting at a redshift of around 0.8, which translates to roughly 7 billion light-years from Earth. The structure wasn't subtle. It stood out clearly in the data once Lopez knew what to look for. And once she'd mapped its full extent, she realized she was looking at one of the largest coherent structures ever detected in the universe. The initial reaction from her colleagues was skepticism. Large-scale structures are common in the universe. Galaxy clusters, superclusters, filaments stretching hundreds of millions of light-years, all of that is well documented and fits comfortably within the standard cosmological model. But there's a limit to how large those structures are supposed to get. That limit has a name. It's called the cosmological principle, and it's one of the foundational assumptions of modern cosmology. The cosmological principle states that on sufficiently large scales, the universe is homogeneous and isotropic. Homogeneous means it looks the same everywhere. Isotropic means it looks the same in every direction. If you zoom out far enough, the thinking goes, all the local clumps and voids and filaments smooth out into a uniform distribution of matter and energy. The principle doesn't claim the universe is perfectly smooth. It just says that the lumpiness averages out once you look at scales larger than a few 100 million light-years. This assumption is baked into the equations of general relativity that cosmologists use to model the universe's expansion. Without it, those equations become vastly more complicated, and the whole enterprise of describing the cosmos with a single set of rules starts to fall apart. The cosmological principle isn't just a nice idea, it's testable. Astronomers have spent decades mapping the distribution of galaxies across the sky, looking for evidence that the universe really does smooth out at large scales, and for the most part it does. Surveys like Sloan have confirmed that once you average over regions larger than about 300 million light-years, the density of matter becomes fairly uniform. There are still fluctuations, but they're small. The universe, at its largest scales, looks more or less the same no matter where you point your telescope, except the Big Ring is 1.3 billion light-years across. That's more than 4 times larger than the scale where the universe is supposed to be smooth. And it's not just big, it's organized. A ring is not a random clump, it's a shape, it has symmetry. It suggests that whatever process formed this structure acted coherently over an enormous volume of space, arranging matter in a way that shouldn't happen if the cosmological principle is correct. Lopez wasn't the first person to find a structure that challenged the principle. In the 1980s, astronomers discovered something called the Great Wall, a vast sheet of galaxies stretching more than 500 million light-years across. At the time, it was considered shockingly large, right at the edge of what the cosmological principle could tolerate. Then in the early 2000s came the Sloan Great Wall, even larger at 1.37 billion light-years. That discovery sparked a round of theoretical hand-wringing, but most cosmologists eventually decided it could be explained as a statistical fluke. If you map enough of the universe, you're bound to find a few unusually large structures just by chance. The universe is lumpy. Sometimes the lumps line up in ways that look impressive but don't actually break the rules. The Big Ring, though, is different. For one thing, it's a ring. The Great Wall and the Sloan Great Wall are elongated structures, filaments or sheets. They're big, but their shapes can be explained by the way matter collapses along the filaments of the cosmic web, the large-scale network of dark matter and gas that threads through the universe. A ring doesn't fit that picture. Rings in cosmology are rare because there's no obvious mechanism that would produce them. Gravitational collapse tends to create filaments and clusters, not circles. For another thing, the Big Ring isn't alone. Around the same time Lopez was analyzing the data for the Big Ring, she found another enormous structure in a nearby region of the sky. She called it the Giant Arc, and we'll come back to that one shortly. But the point is, these structures aren't isolated anomalies. They're sitting relatively close to each other in cosmological terms, at similar distances from Earth, almost as if they're part of a larger pattern. That's harder to write off as a statistical fluke. If you find one unusually large structure, you can call it bad luck. If you find two in the same neighborhood, you have to start asking whether something about your model is wrong. Lopez presented her findings at the 243rd meeting of the American Astronomical Society in January 2024. The response was immediate and divided. Some astronomers were intrigued, others were unconvinced, a few were openly dismissive. The primary criticism was that the Big Ring might not be a real physical structure at all. It could be a projection effect, a chance alignment of unrelated objects that happen to look like a ring when viewed from Earth but have no actual connection in three-dimensional space. Imagine hanging a bunch of Christmas ornaments at different distances in front of a camera. From the camera's perspective, they might form a circle, but that doesn't mean they're physically arranged in a ring. You'd need to move the camera or measure the distances to each ornament independently to know for sure. Lopez anticipated this objection. She and her team ran statistical tests to determine whether the ring could plausibly be a projection artifact. They calculated the probability that the observed distribution of magnesium-2 systems would form a ring-like shape purely by chance. The answer they got was less than 1 in 600. Not impossible, but unlikely enough that calling it a coincidence requires a fair bit of optimism. They also checked whether the ring could be explained by instrumental effects, selection biases, or errors in the distance measurements. None of those explanations held up. The structure appeared to be real. What makes the Big Ring particularly hard to explain is that it doesn't fit any of the standard formation scenarios for large-scale structures. In the early universe, tiny fluctuations in the density of matter, quantum ripples frozen into the fabric of space during the first moments after the Big Bang, grew over time under the influence of gravity. Denser regions pulled in more matter, becoming denser still, eventually collapsing into galaxies and clusters. Less dense regions expanded into voids. The result is the cosmic web, a network of filaments and clusters separated by vast empty spaces. The cosmic web has been mapped in exquisite detail, and its structure matches the predictions of the standard cosmological model almost perfectly. But the cosmic web doesn't make rings, it makes filaments, nodes, and sheets. The geometry is dictated by the way matter collapses under gravity in an expanding universe, and that geometry is not circular. You can get loops in certain rare configurations, but they're small, maybe a few 100 million light-years across at most, and they're not common. A 1.3 billion light-year ring is not something the cosmic web should produce, at least not according to any simulation cosmologists have run. There are a few exotic ideas that could potentially explain ring-like structures at large scales, but none of them are part of the standard model. One possibility involves something called baryonic acoustic oscillations, or BAOs. These are ripples in the distribution of matter left over from sound waves that traveled through the hot plasma of the early universe before atoms formed. BAOs create a characteristic scale in the clustering of galaxies, a preferred distance where you're slightly more likely to find pairs of galaxies separated by about 500 million light-years. They're one of the key pieces of evidence for the standard cosmological model, and they've been measured with high precision in galaxy surveys. But BAOs are subtle statistical effects. They don't create giant visible rings. They're a faint bump in a correlation function, not a coherent physical structure. Another idea points to cosmic strings, hypothetical one-dimensional defects in the fabric of space-time that might have formed during phase transitions in the very early universe. Cosmic strings, if they exist, could be incredibly dense and could theoretically affect the distribution of matter around them. A loop of cosmic string could, in principle, leave a ring-shaped imprint on the large-scale structure of the universe. The problem is that cosmic strings are entirely theoretical. No one has ever detected one, and the energy scales required to produce a cosmic string loop large enough to explain the Big Ring would be absurdly high, far beyond anything the standard model allows. A third possibility, and one that Lopez herself has discussed cautiously, is that the Big Ring could be related to something called conformal cyclic cosmology, a speculative theory proposed by the physicist Roger Penrose. Penrose's idea is that the Big Bang wasn't the absolute beginning of everything, but rather the latest in an infinite series of cycles. According to this model, the universe goes through repeated phases of expansion and collapse, and certain structures from previous cycles could leave imprints on the current one. A ring-like pattern in the distribution of matter might be one of those relics. It's a fascinating idea, and Penrose won a Nobel Prize for his work on black holes, but conformal cyclic cosmology is not widely accepted. It makes predictions that are difficult to test, and most cosmologists remain skeptical. The simplest explanation, the one that doesn't require exotic physics or speculative theories, is that the cosmological principle is wrong. Not catastrophically wrong, but wrong in a specific, important way. Maybe the universe doesn't smooth out at 300 million light-years. Maybe it takes longer, 1 billion light-years or more, for the distribution of matter to become truly uniform. If that's the case, then structures like the Big Ring are just the tail end of the hierarchy of cosmic structure, larger than anything we've seen before, but still part of the same process that builds galaxies and clusters. The problem with this explanation is that it requires rethinking a lot of cosmology. The equations that describe the universe's expansion assume homogeneity at large scales. If that assumption breaks down, then things like the Hubble constant, the age of the universe, and the amount of dark matter and dark energy all need to be recalculated. It's not the end of the world, but it's a headache. What makes the Big Ring especially unnerving for cosmologists is that it's not the kind of problem you can ignore. It's sitting right there in the data, confirmed by multiple independent analyses, with a statistical significance that's hard to dismiss. And it's not a small deviation from the standard model. It's a factor of 4 violation of the scale where the universe is supposed to be homogeneous. That's not a rounding error. That's a red flag. Lopez has been careful in how she talks about the discovery. She hasn't claimed to have overturned the cosmological principle. She hasn't called it a crisis. She's presented the data, outlined the possible explanations, and emphasized that more work is needed. That's the right approach scientifically, but it's also a little frustrating for anyone trying to figure out what this actually means. Is the Big Ring evidence that the standard model is fundamentally flawed, or is it just a really big fluke that will eventually be explained away with better data and more sophisticated modeling? At the moment, no one knows. One thing that does seem clear is that the universe is more structured at large scales than cosmologists expected. The Big Ring is the most dramatic example, but it's not the only one. Webb's early galaxy findings, the oversized black holes, the unexpectedly mature galaxies in the first few 100 million years after the Big Bang, all of that points in the same direction. The universe assembled itself faster and more efficiently than the models predicted. And if it could do that in the early universe, maybe it's also capable of organizing matter into enormous coherent structures later on, structures that shouldn't exist according to the rules we've been using for the past century. There's a broader question lurking underneath all of this, one that cosmologists don't like to talk about too much because it's uncomfortable. How much of what we think we know about the universe is actually constrained by observations, and how much is just us assuming that the math we like is the math that nature uses? The cosmological principle is elegant. It makes the equations tractable. It allows cosmologists to model the entire universe with a handful of parameters. But elegance is not evidence. The universe is under no obligation to be simple or to play by rules that make our lives easier. If large-scale structure violates the cosmological principle, then the universe is messier than we thought, and the project of describing it with a single unified model gets a lot harder. Lopez's discovery raises another uncomfortable possibility. What if the Big Ring isn't unusual? What if there are other structures out there just as large or larger that we haven't noticed yet because we haven't looked in the right places or with the right techniques? The Sloan survey has mapped a huge fraction of the sky, but it's not complete. There are regions that haven't been surveyed in as much detail, regions where something like the Big Ring could be hiding. Webb is now adding to that picture, finding objects at distances and scales that ground-based surveys can't reach. If the early universe was capable of producing massive galaxies in a few 100 million years, maybe the later universe was capable of organizing matter into structures even larger than the Big Ring. We won't know until we look, and that brings us to the next piece of the puzzle. Because the Big Ring, as strange as it is, isn't the only enormous structure Lopez found. Sitting almost next to it in the sky, at a similar distance, is another object that stretches the limits of what cosmology says should be possible. It's called the Giant Arc, and unlike the Big Ring, which at least has the decency to be vaguely circular, the Giant Arc is just a straight-up wall, a cosmic barrier more than 3 billion light-years long, slicing through space like someone drew a line with a ruler and forgot to stop. If the Big Ring raised questions, the Giant Arc is about to turn those questions into demands. And that brings us to the next piece of the puzzle. Because the Big Ring, as strange as it is, isn't the only enormous structure Lopez found. Sitting almost next to it in the sky, at a similar distance, is another object that stretches the limits of what cosmology says should be possible. It's called the Giant Arc, and unlike the Big Ring, which at least has the decency to be vaguely circular, the Giant Arc is just a straight-up wall, a cosmic barrier more than 3 billion light-years long, slicing through space like someone drew a line with a ruler and forgot to stop. Lopez discovered the Giant Arc first, actually back in 2021, a full 3 years before she announced the Big Ring. She was using the same technique, mapping magnesium-2 absorption systems in quasar spectra from the Sloan survey, tracing where gas and galaxies clumped together across billions of light-years of space. The arc showed up as a sweeping, elongated overdensity stretching across roughly 15 degrees of sky when viewed from Earth. 15 degrees is about 30 times the width of the full moon. Picture holding your fist at arm's length. The arc spans roughly the distance from your thumb to your pinky, but that's just the angular size. The actual physical length, once you account for how far away it is, comes out to about 3.3 billion light-years from one end to the other. 3.3 billion light-years. Let's sit with that number for a second. The Milky Way, our entire galaxy, is about 100,000 light-years across. The local group, the collection of galaxies that includes the Milky Way, Andromeda, and a few dozen smaller galaxies spans roughly 10 million light-years. The Virgo supercluster, the enormous collection of galaxy groups and clusters that our local group belongs to, is about 110 million light-years wide. The giant arc is 30 times larger than that. If you shrank the Virgo supercluster down to the size of a basketball, the giant arc would stretch from Boston to Miami, and it's not a loose, diffuse cloud of galaxies scattered randomly over that distance. It's a coherent structure, a connected arrangement of matter that appears to trace out a single continuous feature across a vast swath of the universe. When Lopez first presented the giant arc at the 238th meeting of the American Astronomical Society in June 2021, the reaction was similar to what she'd later get for the Big Ring: fascination mixed with skepticism. Some astronomers were excited. Others questioned whether the structure was real or just a statistical artifact, a random alignment that looked meaningful but didn't correspond to any actual physical connection between the galaxies involved. The same criticisms that would later be leveled at the Big Ring applied here. Could this just be a projection effect? Could it be a chance clustering that happened to line up in a way that looked like an arc from our perspective? Lopez ran the numbers. She and her collaborators calculated the probability that the observed distribution of magnesium-2 systems would form an arc-like shape purely by chance. The odds came out to less than 1 in 4,000. Not impossible, but unlikely enough that dismissing it as coincidence requires a degree of confidence that most scientists aren't comfortable committing to. They also checked whether the arc could be explained by instrumental biases, errors in the spectroscopic measurements, or selection effects in how the quasars were chosen for observation. None of those explanations worked. The structure appeared to be real, sitting at a redshift of around 0.8, the same distance as the Big Ring, roughly 7 billion light-years from Earth. The giant arc and the Big Ring are neighbors. That's the part that makes this whole thing exponentially harder to explain. If you found one enormous anomalous structure somewhere in the observable universe, you could argue that it's a statistical outlier, a 1 in a million fluke that you happened to catch because astronomers have now mapped enough of the sky that even very rare events should show up occasionally. That argument gets a lot weaker when you find two such structures sitting right next to each other. The Big Ring spans about 1.3 billion light-years. The giant arc spans 3.3 billion, and they're separated by only a few 100 million light-years in three-dimensional space. In cosmological terms, they're practically on top of each other. Picture a map of your country. Now imagine finding a mountain range that's 3 times longer than any mountain range that's supposed to exist, and right next to it, a perfectly circular lake that's also far too large to fit any known geological formation process. You could maybe explain one of them as a weird edge case. Explaining both of them in the same region starts to feel like the map itself might be missing something important. That's where cosmology is right now with the giant arc and the Big Ring. One anomaly is strange. 2 anomalies in the same neighborhood is a pattern. The giant arc's shape is different from the Big Ring's, but it's no less problematic. Arcs and filaments are common in the large-scale structure of the universe. The cosmic web, that vast network of matter threading through space, is full of elongated features where galaxies line up along filaments of dark matter. What makes the giant arc unusual is its length. Most filaments in the cosmic web stretch for a few 100 million light-years, maybe up to 1 billion in extreme cases. 3 billion light-years is off the chart. It's longer than any filament that standard cosmological simulations predict should exist. There's another issue. The giant arc isn't just long, it's coherent. If you look at the distribution of galaxies and gas along its length, they're not randomly scattered. They trace out a smooth, continuous curve. That's hard to explain if the structure is just a chance alignment of unrelated objects. Chance alignments tend to be messy, with gaps and irregularities. The giant arc looks organized, like something that formed as a single connected structure and has been sitting there for billions of years, quietly defying the rules. The same formation mechanisms that struggle to explain the Big Ring also struggle here. The cosmic web doesn't produce features this large. Gravitational collapse in an expanding universe creates a hierarchy of structures, starting with small clumps that merge into larger ones over time. But there are limits to how large those structures can grow before the expansion of space itself pulls them apart faster than gravity can hold them together. By the time you get to scales of a few 100 million light-years, the expansion starts winning. Structures stop growing, they freeze in place, and the universe around them keeps expanding. A 3 billion light-year arc shouldn't have had time to form, not in the 13.8 billion years since the Big Bang, and not in a universe that's been accelerating its expansion for the past 5 billion years. One possibility that's been floated is that the giant arc isn't a single structure at all, but rather a series of smaller structures that happen to line up in a way that makes them look connected from our vantage point. Imagine a string of Christmas lights hanging in a dark room. From one angle, they might look like a continuous glowing line. From another angle, you'd see the gaps between the individual bulbs. Maybe the giant arc is like that, a series of galaxy clusters and filaments that are only loosely associated but appear connected because of the way we're looking at them. The problem with that explanation is that Lopez's analysis didn't just identify the arc by eye. She used statistical methods to test whether the distribution of magnesium-2 systems showed a significant overdensity along the arc compared to the surrounding regions. The answer was yes. There's more matter along that line than there should be if it were just a random assortment of unrelated objects. That doesn't prove it's a single physically connected structure, but it does suggest that whatever process created the arc involved some kind of coherent influence acting over an enormous volume of space. Another idea points to baryonic acoustic oscillations again, those subtle ripples in the distribution of matter left over from the early universe. Baryons create a preferred scale of clustering, a characteristic distance where galaxies are slightly more likely to bunch together. But baryons are statistical effects, tiny bumps in the correlation function when you average over millions of galaxies. They're not supposed to produce visible structures, and they certainly aren't supposed to produce anything 3 billion light-years long. Trying to explain the giant arc with baryons is like trying to explain a mountain range by pointing to the texture of the sand on a beach. The scales don't match. Cosmic strings, those hypothetical defects in space-time, could potentially leave large-scale imprints on the distribution of matter, but the same objections apply here as they do for the Big Ring. Cosmic strings are speculative, no one has detected one, and producing a structure the size of the giant arc would require energy scales far beyond anything the standard model allows. You'd need exotic physics operating in the early universe, and there's no independent evidence that such physics exists. The more exotic explanation, the one that keeps surfacing in conversations about both the arc and the ring, is that these structures are remnants from a previous cycle of the universe, echoes of an earlier cosmic epoch that somehow survived the Big Bang and got imprinted onto the current distribution of matter. Roger Penrose's conformal cyclic cosmology predicts exactly this kind of thing. According to Penrose, the universe has gone through an infinite series of expansions and collapses, and certain features from one cycle can leave traces in the next. A giant arc or ring could be one of those traces, a scar from a previous universe encoded into the structure of ours. It's a beautiful idea, and Penrose is a brilliant physicist, but conformal cyclic cosmology is not mainstream. It makes predictions that are difficult to test, and most cosmologists remain unconvinced. The theory requires the universe to have specific properties that aren't obviously true, and it doesn't easily fit with the standard inflationary model of the Big Bang, which has been extraordinarily successful at explaining almost everything else we observe. Invoking conformal cyclic cosmology to explain the giant arc and the Big Ring is a bit like invoking a completely new branch of physics to explain why your car won't start. Maybe it's necessary, but you'd want to check the battery first. The simplest explanation, once again, is that the cosmological principle breaks down at larger scales than anyone expected. Maybe the universe doesn't smooth out at 300 million light-years. Maybe it takes 1 billion light-years, or 3 billion or more. If that's true, then the giant arc and the Big Ring are just the largest members of a hierarchy of structures that extends much further than the current models predict. The universe is lumpier than we thought, and the scale at which it becomes homogeneous is much larger than the scale we've been assuming for the past century. This explanation has the advantage of not requiring any new physics. It just requires accepting that one of the foundational assumptions of cosmology, the idea that the universe is homogeneous on large scales, is wrong in a specific and quantifiable way. The downside is that it makes cosmology much harder. If the universe isn't homogeneous on the scales we've been modeling, then all the equations that describe its expansion need to be revisited. The Hubble constant, the density of dark matter, the amount of dark energy, the age of the universe, all of those parameters are calculated under the assumption that the cosmological principle holds. If it doesn't, then everything downstream of that assumption is suspect. Cosmologists hate this kind of thing because it's a can of worms. Once you start questioning foundational assumptions, it's hard to know where to stop. If the cosmological principle is wrong, what else might be wrong? Are the assumptions about dark matter correct? Is dark energy really a constant, or does it vary with time or location? Is general relativity itself the right framework for describing the universe at the largest scales, or do we need a new theory of gravity? These are not small questions. They're the kind of questions that keep theoretical physicists employed for decades, but they're also the kind of questions that can make the entire field feel like it's standing on quicksand. What makes the giant arc particularly frustrating for cosmologists is that it's not even the first time something like this has been found. There have been other reports of unusually large structures over the years: the Great Wall in the 1980s, the Sloan Great Wall in the early 2000s, the Huge Large Quasar Group, a collection of 73 quasars spanning 4 billion light-years, discovered in 2013. Each time one of these structures was announced, there was a flurry of excitement and debate. Some researchers argued that they violated the cosmological principle. Others argued that they were statistical flukes or artifacts of the way the surveys were conducted. Eventually, the controversy would die down. The structure would be noted in the literature as an interesting anomaly, and everyone would move on. The difference this time is that the anomalies are piling up too fast to ignore. The giant arc, the Big Ring, the impossibly massive galaxies Webb found in the early universe, the oversized black holes, the unexpectedly high expansion rate measured by the SH0ES team. Every one of these findings, taken individually, could be explained away with enough effort, but taken together they paint a picture of a universe that's behaving in ways the standard model doesn't predict, and at some point you have to stop calling them anomalies and start calling them data. Lopez has been careful not to overstate her findings. In interviews and conference talks, she emphasizes that the giant arc and the Big Ring don't disprove the cosmological principle. They challenge it. They raise questions. They suggest that the scale at which the universe becomes homogeneous might be larger than previously thought. But she stops short of claiming that the standard model is wrong. That's the right approach scientifically, but it also leaves the field in a kind of limbo. If these structures are real, and if they're not statistical flukes, then something about our understanding of large-scale structure formation is incomplete. But what exactly? And how do you fix it without tearing down the entire framework of modern cosmology? One thing that does seem clear is that the giant arc and the big ring are forcing cosmologists to take seriously the possibility that the universe is more complex at large scales than the models predict. The standard cosmological model, sometimes called lambda CDM, is extraordinarily successful. It explains the cosmic microwave background, the distribution of galaxies, the abundance of light elements, the accelerating expansion of the universe, all with just 6 free parameters. It's one of the most successful scientific theories ever developed. But it's built on assumptions, and one of those assumptions is that the universe smooths out on large scales. If that assumption is wrong, then lambda CDM doesn't collapse entirely, but it does need to be modified. And modifications are tricky because they tend to have unintended consequences. Change one thing, and you might break something else that was working perfectly. The giant arc also raises a more philosophical question. How much of what we think we know about the universe is constrained by actual observations, and how much is just us assuming that the math we like is the math that nature uses? The cosmological principle is elegant. It makes the equations simple. It allows cosmologists to describe the entire universe with a handful of numbers. But elegance is not evidence. The universe doesn't care whether our equations are easy to solve. If the giant arc and the big ring are telling us that the universe is messier and more complicated than we thought, then we need to accept that and deal with the consequences, even if it makes our lives harder. There's also the uncomfortable possibility that the giant arc and the big ring are not the largest structures out there. The Sloan survey has mapped a huge fraction of the sky, but it's not complete. There are regions that haven't been surveyed in as much detail, regions where something even larger could be hiding. And now that Webb is operational, it's adding entirely new data at distances and resolutions that ground-based surveys can't reach. If the early universe was capable of producing massive galaxies in a few 100 million years, maybe the later universe was capable of organizing matter into structures even larger than the giant arc. We won't know until we look. The relationship between the giant arc and the big ring is what makes this discovery so difficult to dismiss. If Lopez had found just the arc, or just the ring, skeptics could argue that it's a statistical fluke, one extreme outlier in a universe large enough that extreme outliers should occasionally appear. But finding both structures in the same region of space, at the same distance, with similar observational signatures, makes the fluke explanation much harder to defend. The odds of finding one structure that large are already slim. The odds of finding two sitting next to each other are vanishingly small, unless there's something about that region of the universe, or about the universe in general, that makes such structures more common than the models predict. And that brings us back to the core issue. These structures shouldn't exist, not according to the rules cosmologists have been using for nearly a century. The cosmological principle says the universe should be smooth on scales larger than a few 100 million light-years. The giant arc is 10 times larger than that. The big ring is 4 times larger. Together they span a region of space that dwarfs anything the standard model predicts. And they're not diffuse, barely there statistical blips. They're coherent, organized, and sitting in a dataset that's been cross-checked and validated by multiple independent teams. So either the data is wrong, which seems increasingly unlikely given how many times it's been verified, or the theory is wrong, which is the possibility that no one in the field particularly wants to confront but is becoming harder to avoid. The cosmological principle has been a cornerstone of cosmology since the 1920s. It's embedded in every textbook, every simulation, every model of the universe's evolution. If it breaks down at scales of 1 billion light-years or more, then every prediction that relies on it needs to be revisited. And that's a monumental task, the kind of thing that could occupy the entire field for the next decade or longer. The giant arc, like the Big Ring, is not going away. It's sitting there in the Sloan data, confirmed by independent analyses, with a statistical significance that's hard to dismiss. And now that cosmologists know what to look for, they're starting to find hints of other large-scale structures that might be similarly problematic. The universe, it turns out, is full of surprises. Some of those surprises fit neatly into the existing framework. Others, like the giant arc, refuse to cooperate. And when your observations consistently refuse to cooperate with your theory, eventually you have to ask whether the problem is with the observations or with the theory. That question is about to get a lot more urgent, because the giant arc and the Big Ring aren't just interesting anomalies. They're direct challenges to one of the most specific and quantifiable predictions of modern cosmology. There's a number, a hard limit, on how large structures are supposed to get before the cosmological principle kicks in and smooths everything out. That number is 1.2 billion light-years. The giant arc is nearly 3 times larger. The Big Ring is bigger than the limit. And the fact that both structures exist, confirmed and measured, sitting in the same cosmic neighborhood, means cosmologists can no longer pretend this is a minor problem that will go away with better data. The limit has been broken. The question now is what that means for everything else we think we know about how the universe is built, and whether the rules we've been using for the past century are still the right rules at all. That question is about to get a lot more urgent, because the giant arc and the Big Ring aren't just interesting anomalies, they're direct challenges to one of the most specific and quantifiable predictions of modern cosmology. There's a number, a hard limit, on how large structures are supposed to get before the cosmological principle kicks in and smooths everything out. That number is 1.2 billion light-years. The giant arc is nearly 3 times larger. The Big Ring exceeds it comfortably. And the fact that both structures exist, confirmed and measured, sitting in the same cosmic neighborhood, means cosmologists can no longer pretend this is a minor problem that will go away with better data. The limit has been broken. The question now is what that means for everything else we think we know about how the universe is built. So where does that 1.2 billion light-year limit come from? It's not arbitrary. It's not a number someone pulled out of thin air because it sounded reasonable. It's a direct consequence of the physics that governs how structures form in an expanding universe, and it's baked into the standard model of cosmology that's been guiding the field for decades. To understand why the Big Ring and the giant arc are considered impossible, you need to understand what prevents the universe from building anything larger than that limit. And the answer comes down to 3 things: the speed of light, the age of the universe, and the rate at which gravity can pull matter together before the expansion of space tears it apart. Start with the speed of light. Light travels at about 300,000 kilometers per second. That's fast by any human measure. But the universe is enormous, and even light takes time to cross cosmic distances. A light year, the distance light travels in 1 year, is about 9.5 trillion kilometers. That's the baseline unit astronomers use when talking about anything beyond our solar system. The nearest star to the Sun is a little over 4 light-years away. The Milky Way galaxy is about 100,000 light-years across. The Andromeda Galaxy, our nearest large neighbor, is about 2.5 million light-years from Earth, and the observable universe, the sphere of space from which light has had time to reach us since the Big Bang, spans about 93 billion light-years in diameter. That last number sounds confusing because the universe is only about 13.8 billion years old. If light has only been traveling for 13.8 billion years, how can the observable universe be 93 billion light-years across? The answer is expansion. Space itself has been stretching the entire time that light has been traveling through it, so objects that were much closer when they emitted the light we're seeing now have since moved much farther away. The observable universe is bigger than its age in light-years would suggest because the ruler itself has been getting longer. But here's the thing. Expansion doesn't just make the universe bigger, it also makes it harder for gravity to pull things together. In the early universe, when everything was much closer together and much denser, gravity had the upper hand. Tiny fluctuations in the density of matter, quantum ripples frozen into space during the first moments after the Big Bang, grew over time as denser regions pulled in more matter and became denser still. Those regions eventually collapsed into the first stars, then galaxies, then clusters of galaxies, building up the cosmic web we see today. But there's a limit to how large those structures can grow, because at some point the expansion of the universe becomes strong enough that it pulls matter apart faster than gravity can draw it together. Think of it like trying to build a sandcastle on a beach while the tide is coming in. If you work fast and the sand is damp enough to hold together, you can build a decent structure before the waves reach you. But if you try to build something too large, or if you work too slowly, the tide will wash away the outer parts of your castle before you can finish. Gravity is the force trying to build the castle. Expansion is the tide. And the age of the universe sets the clock for how much time you have to work. The standard cosmological model, lambda CDM, describes this process in detail. Lambda refers to dark energy, the mysterious force that's been accelerating the expansion of the universe for the past 5 billion years or so. CDM stands for cold dark matter, the invisible substance that makes up about 85% of the matter in the universe and provides the gravitational scaffolding that holds galaxies and clusters together. Lambda CDM has been extraordinarily successful. It explains the cosmic microwave background, the distribution of galaxies, the abundance of light elements like hydrogen and helium, the large-scale structure of the universe, all with just 6 free parameters. It's one of the crown jewels of modern physics. But lambda CDM makes very specific predictions about how large structures can grow. According to the model, there's a maximum size for gravitationally bound structures, regions of space where gravity has managed to pull matter together tightly enough that the internal motions of galaxies and clusters overcome the expansion of space. Beyond that size, expansion wins. Matter gets pulled apart before gravity can organize it into a coherent structure. The limit depends on how much time has passed since the Big Bang, how fast the universe has been expanding, and how much dark matter is available to provide the gravitational pull. Run the numbers, plug in the observed values for the density of matter and the strength of dark energy, and you get a maximum size of about 1.2 billion light-years for structures that can form within the 13.8 billion year history of the universe. That number isn't written on a stone tablet somewhere. It's an estimate, and different calculations can give slightly different values depending on the assumptions you make. But the order of magnitude is solid. Structures larger than about 1 billion light-years shouldn't have had time to form. The universe simply hasn't been around long enough for gravity to do the necessary work at those scales. The expansion of space, especially the accelerated expansion driven by dark energy over the past 5 billion years, should have prevented anything bigger from assembling. Now look at what Lopez found. The Big Ring is 1.3 billion light-years across. That's already over the limit, but not by a huge margin. You could maybe argue that the limit is a little soft, that the real number is closer to 1.5 billion light-years if you tweak the assumptions slightly, and the Big Ring just barely squeaks in under the wire. It would be uncomfortable, but not catastrophic. The giant arc, though, is 3.3 billion light-years across. That's not close. That's not a marginal violation. That's nearly 3 times the size that lambda CDM says should be possible. And it's not just a loose cloud of galaxies scattered randomly across that distance. It's a coherent structure, an organized arrangement of matter that appears to trace out a single continuous feature. How do you build something that large in a universe that's only 13.8 billion years old? Let's do the math in the most generous way possible. Assume that the giant arc started forming as soon as it physically could, right after the cosmic dark ages ended and the first stars began lighting up the universe. That's about 200 to 400 million years after the Big Bang. Let's be extremely generous and say it started at 200 million years. That gives it 13.6 billion years to grow. Now assume that matter is falling together at the maximum speed gravity can manage without violating any known physics. How large a structure can you build in that time? The answer depends on how fast matter can move. In the early universe, before dark energy started accelerating the expansion, matter could fall together at speeds of a few hundred kilometers per second, maybe up to 1,000 in the densest regions. Let's be absurdly optimistic and say matter was moving at 1,000 kilometers per second, which is faster than almost anything observed in the local universe, but not impossible in principle. At that speed, over 13.6 billion years, matter could travel about 13.6 billion light-years. But that's one direction. To build a structure 3.3 billion light-years across, you need matter to fall together from both sides, meeting somewhere in the middle. So cut the distance in half. Matter falling in from opposite directions at 1,000 kilometers per second could, over the entire history of the universe, build a structure about 27 billion light-years across. Okay, so that's comfortably larger than 3.3 billion light-years. Problem solved, right? Not even close. Because that calculation assumes that matter has been falling together at maximum speed in a straight line with no interference for the entire history of the universe. It assumes no expansion working against it, no dark energy pushing it apart, no turbulence or random motion spreading things out. It assumes a universe that's basically a frictionless vacuum where gravity has nothing to fight against. That universe does not exist. In the real universe, the one we actually live in, matter doesn't fall together in straight lines at constant speed. It gets slowed down by pressure, by random thermal motion, by the expansion of space pulling everything apart. And for the past 5 billion years, dark energy has been actively accelerating that expansion, making it even harder for gravity to pull matter together. Once you account for all of that, the maximum size for a structure drops dramatically. The 1.2 billion light-year limit isn't a conservative estimate. It's what you get when you run realistic simulations of structure formation in a lambda CDM universe, using the observed values for matter density, dark energy, and the Hubble constant. It's the size at which gravity loses the fight against expansion. Anything larger than that shouldn't have had time to collapse into a coherent structure. It should still be in the process of coming together, or more likely, it should have been pulled apart by expansion before it ever finished forming. The giant arc doesn't care. It's sitting there in the data, 3.3 billion light-years across, fully formed, organized, coherent. The Big Ring is right next to it, 1.3 billion light-years across, also fully formed, also organized. Both of them are at a redshift of about 0.8, which means we're seeing them as they existed roughly 7 billion years ago when the universe was only about half its current age. That makes the problem worse, not better. If these structures exist now, then they had to have started forming even earlier, which gives them even less time to assemble before the expansion of space and the acceleration from dark energy made further growth impossible. So either the structures aren't real, which seems increasingly unlikely given how thoroughly they've been analyzed, or something about the standard model is wrong. Maybe the universe is older than we think, which would give structures more time to form, but we know the age of the universe pretty precisely from multiple independent measurements. The cosmic microwave background gives 13.8 billion years. The oldest stars we've found are consistent with that age. The abundances of radioactive elements in meteorites point to the same timeline. There's not a lot of wiggle room there. You can't just add a few billion years to make the math work without breaking a dozen other things that are currently explained perfectly well. Maybe the expansion rate was different in the past. If the universe expanded more slowly during the period when these structures were forming, gravity would have had an easier time pulling matter together. But again, we have measurements of the expansion rate at different times in the universe's history, and they match the predictions of lambda CDM almost perfectly. The cosmic microwave background, the distribution of galaxies, the distances to supernovae, they all tell a consistent story about how fast the universe has been expanding. You can't tweak the expansion rate enough to explain the giant arc without making the cosmic microwave background look wrong, and the cosmic microwave background is one of the most precisely measured quantities in all of science. Maybe there was more dark matter in the region where these structures formed, which would have provided extra gravitational pull to help them grow faster. That's possible in principle, but it creates its own problems. Dark matter is supposed to be distributed fairly evenly across the universe on large scales. That's one of the key predictions of the cosmological principle. If you concentrate enough dark matter in one region to build a structure as large as the giant arc, you're creating an enormous overdensity that shouldn't exist according to the same models that predict the 1.2 billion light-year limit in the first place. You're solving one problem by creating another. Maybe the structures aren't gravitationally bound at all. Maybe they're just transient features, patterns in the distribution of matter that look organized from our perspective, but aren't actually held together by gravity. That would get around the formation timescale problem, because you wouldn't need gravity to pull matter together over billions of years. You just need some process that could create large-scale patterns in the initial distribution of matter, and those patterns would persist even as the universe expanded. The trouble is, we don't know of any process that could create patterns this large and this coherent. The fluctuations in the cosmic microwave background, the tiny density variations that seeded all the structure we see today, have a characteristic scale of about a few 100 million light-years. Patterns larger than that should have been smoothed out by the expansion of the universe before they ever had a chance to become visible. And even if such patterns existed, they would be statistical, not geometric. You wouldn't expect to see clean arcs or rings. You'd expect to see noise. One of the more exotic ideas is that the Big Ring might be related to baryonic acoustic oscillations, or BAOs. These are ripples in the distribution of matter left over from sound waves that traveled through the hot plasma of the early universe before atoms formed. BAOs create a preferred distance scale, a characteristic separation of about 500 million light-years, where galaxies are slightly more likely to cluster together. If you squint hard enough, you could imagine that the Big Ring is some kind of BAO feature, a spherical shell of matter that formed around one of those ripples and somehow remained coherent over billions of years. But the analysis done by Lopez and her team specifically ruled that out. The Big Ring is too large to be a BAO feature. BAOs create small statistical bumps in the distribution of galaxies, not billion light-year structures, and the Big Ring isn't spherical, which BAO features are supposed to be. It's a ring which is a completely different geometry. The more you look at the details, the more uncomfortable the situation becomes. These structures are not minor deviations from the standard model. They're not things that can be explained away by adjusting a parameter here or tweaking an assumption there. They're direct violations of a core prediction of lambda CDM, the prediction that structures larger than about 1.2 billion light-years shouldn't exist because there hasn't been enough time for gravity to build them. And they're not alone. The Sloan Great Wall, discovered in the early 2000s, is about 1.4 billion light-years across. The huge Large Quasar Group, found in 2013, spans about 4 billion light-years. Every few years, astronomers seem to find another structure that's larger than the limit says it should be. Each time there's a flurry of debate, and each time the field eventually decides that the discovery is either a statistical fluke or an artifact of how the structure is being defined. But at some point, you run out of flukes. Alexia Lopez, in interviews about her discoveries, has been careful but direct. She said that the Big Ring and the giant arc lead to the ultimate question: do we need a new standard model? That's not a question anyone asks lightly. The standard model of cosmology has been tested and validated in dozens of different ways over the past several decades. It explains an enormous range of observations with remarkable precision. Suggesting that it might need to be replaced or fundamentally revised is not something you do unless the evidence is overwhelming. But Lopez is asking the question, and she's not the only one. Other researchers looking at Webb's early galaxy data, at the unexpectedly massive black holes, at the too-fast expansion rate measured by the SH0ES team, are starting to ask the same thing: how many anomalies can a model absorb before it stops being the standard? The 1.2 billion light-year limit is not the only pillar of lambda CDM, but it's an important one. It's a direct consequence of the interplay between gravity and expansion, two of the most fundamental forces shaping the universe. If structures significantly larger than that limit exist, and if they're not statistical artifacts or projection effects, then one of three things has to be true. Either gravity is stronger than we think on very large scales, which would require modifying general relativity, or the expansion of the universe has been slower than we think, which would require revising the entire timeline of cosmic history. Or the initial conditions of the universe, the distribution of matter and energy right after the Big Bang, were different from what we've been assuming, which would require rethinking inflation and the origin of cosmic structure. None of those options are easy. All of them have consequences that ripple through the rest of cosmology. There's also the uncomfortable possibility that the cosmological principle itself is wrong at these scales. If the universe is not homogeneous on scales larger than 1 billion light-years, then the assumption that it's the same everywhere breaks down. And if that assumption breaks down, then the equations that describe the universe's expansion, which rely on that assumption, stop being valid. You'd need a new set of equations, ones that can handle an inhomogeneous universe, and those equations would be vastly more complicated. Instead of describing the entire cosmos with a handful of parameters, you'd need a different description for every region of space. Cosmology would become more like weather forecasting, trying to model a complex, chaotic system that behaves differently in different places. That's not a future most cosmologists are eager to embrace. The core of the problem is time. 13.8 billion years sounds like a long time, and by human standards it is. But for building structures on cosmic scales, it's not that long. Gravity is patient, but it's also slow. It takes millions of years for a cloud of gas to collapse into a star. It takes billions of years for galaxies to merge and form clusters. The universe has had enough time to build the structures we see in our local neighborhood, the galaxy clusters, the superclusters, the filaments of the cosmic web. But it should not have had enough time to build anything as large as the giant arc or the Big Ring. The clock runs out, expansion wins, and yet there they are. What makes this particularly frustrating is that we can't just build these structures in a computer simulation and see what happens. Simulating the formation of cosmic structure is one of the most computationally intensive tasks in all of science. You have to track the motion of billions of particles under the influence of gravity, dark matter, gas pressure, and the expansion of space, all evolving over billions of years of cosmic time. The largest simulations currently running use supercomputers and take months to complete. And even those simulations don't produce structures as large as the giant arc. They produce galaxy clusters, filaments, voids, all the features of the cosmic web that match observations beautifully, but nothing remotely close to 3 billion light-years across. The simulations are telling us the same thing the theory is telling us. These structures shouldn't exist. The missing puzzle piece is what's driving researchers crazy. There's clearly something about large-scale structure formation that the models aren't capturing. Maybe it's a process that only operates on the largest scales, something that becomes important when you're dealing with regions of space billions of light-years across, but is negligible at smaller scales. Maybe it's a relic of the very early universe, some feature imprinted during inflation that we haven't accounted for. Maybe it's related to dark energy in a way we don't understand, some interaction between dark energy and dark matter that affects how structures grow over time. Or maybe it's something else entirely, something no one has thought of yet because we've never had data this precise at these scales before. Webb and the Sloan survey are giving us that data now. And the data is telling us that the universe at its largest scales is not behaving the way lambda CDM predicts. The Big Ring and the giant arc are the most dramatic examples, but they're part of a broader pattern. The early massive galaxies, the oversized black holes, the Hubble tension. All of these findings point in the same direction. The universe assembled itself faster and organized itself more coherently than the standard model says it should have. Something about our picture of cosmic history is incomplete, and whatever that something is, it's becoming harder to ignore with every new observation. The question cosmologists are now facing is whether these anomalies can be absorbed into the existing framework with minor modifications, or whether they're signaling the need for a more fundamental rethinking of how the universe works. The Big Ring and the giant arc, sitting there in the data, coherent and undeniable, are forcing that question into the open. The 1.2 billion light-year limit has been broken. And if the limit is wrong, then the whole structure of predictions built on top of it might be shaky too. The universe is telling us something. The challenge is figuring out what it's trying to say before the pile of impossible discoveries grows too large to manage. And those discoveries are still coming. Because while cosmologists have been wrestling with structures that are too large, Webb has been finding objects that are too old, galaxies that existed too soon after the Big Bang, galaxies that contain stars older than the universe should have allowed them to form. If the giant arc breaks the rules of space, Webb's early galaxies are about to break the rules of time. And those discoveries are still coming, because while cosmologists have been wrestling with structures that are too large, Webb has been finding objects that are too old. Galaxies that existed too soon after the Big Bang, galaxies that contain stars older than the universe should have allowed them to form. If the giant arc breaks the rules of space, Webb's early galaxies are about to break the rules of time. The first hints came in the summer of 2022, just weeks after Webb released its initial deep-field images. A team analyzing the data flagged 6 candidate galaxies that appeared to have formed between 500 and 700 million years after the Big Bang. That timeline alone was startling. 500 million years is less than 4% of the universe's current age. In cosmic terms, it's infancy. The universe at that point was still cooling down from its explosive beginning, still figuring out how to build the first generation of stars. Finding fully formed galaxies that early was like excavating a construction site and discovering a skyscraper foundation in a layer of bedrock that predates the invention of concrete. What made these galaxies genuinely shocking wasn't just their age, it was their maturity. Some of them appeared to rival the Milky Way in mass, containing hundreds of millions, possibly billions of stars. Our own galaxy took more than 13 billion years to assemble itself into its current form, accreting gas and smaller galaxies piece by piece, building up its spiral arms and central bulge through countless mergers and slow gravitational collapse. These 6 objects, if the measurements held, had done something similar in 1/10 of the time. One researcher described them as universe breakers, not because they literally broke the universe, but because they broke every model cosmologists had spent decades building to explain how galaxies form. Let's talk about what it takes to build a galaxy. You start with a cloud of gas, mostly hydrogen with a bit of helium, sitting in a region of space where dark matter has begun to clump together under its own gravity. The dark matter acts as scaffolding, pulling ordinary matter inward. As the gas falls into the dark matter halo, it heats up from the compression. Eventually, it gets dense enough and hot enough in certain pockets that nuclear fusion ignites. Stars are born. Those stars burn for millions or billions of years, fusing hydrogen into heavier elements deep in their cores. When the most massive stars die, they explode as supernovae, scattering those heavier elements into the surrounding gas. From that enriched material, a new generation of stars forms, this time with traces of carbon, oxygen, nitrogen, iron, all the elements that make planets and eventually life possible. This process takes time, a lot of time. The first stars, the ones astronomers call population 3 stars, were likely enormous, hundreds of times the mass of our Sun, burning so hot and so fast that they lived for only a few million years before going supernova. From their ashes came the second generation, slightly smaller, slightly longer lived. Then the third generation and the fourth, each one enriching the interstellar medium with more heavy elements. Galaxies don't just appear fully formed, they grow in stages, each stage building on the previous one, each stage requiring millions of years to complete. The standard model of galaxy formation predicts that the first true galaxies, collections of billions of stars organized into coherent structures, shouldn't have appeared until at least 1 billion years after the Big Bang, possibly longer. Webb was finding them at 500 million years. That's half the time the models say they need. And they weren't small, dim proto-galaxies barely holding themselves together. They were bright. They had structure. Some of them showed signs of disc-like shapes or early spiral arms, features that are supposed to take billions of years to develop. The light Webb was detecting from these galaxies had been traveling toward Earth for more than 13 billion years. By the time it reached the telescope's mirror, it had been stretched so dramatically by the expansion of space that wavelengths that started out as ultraviolet had arrived as infrared. That stretching is what allows astronomers to calculate how far away and how old the galaxies are. The more the light is stretched, the redshift, the farther back in time you're looking. The 6 initial candidates had redshifts ranging from about 10 to 13. Redshift 13 corresponds to light that left its source when the universe was only about 330 million years old. 330 million years sounds like a long time until you remember that our Sun is 4.6 billion years old and will live for another 5 billion before it dies. 330 million years is barely enough time for the first stars to ignite, live their brief violent lives, and explode. It's certainly not enough time for multiple generations of stars to form, die, and enrich the surrounding gas to the point where you can build a galaxy containing billions of stars. And yet there they were, fully assembled, shining brightly enough to be detected across nearly the entire observable universe. The reaction from the astronomy community was immediate and split. Some researchers were thrilled. This was exactly the kind of discovery Webb had been built to make, finding things that didn't fit, pushing the boundaries of what the models predicted. Others were skeptical. Redshift estimates based on photometry, measuring the colors of light in different filters, can be tricky. If you misidentify a spectral line, or if dust inside the galaxy absorbs certain wavelengths and re-emits them at longer ones, you can place an object much farther back in time than it actually is. The 6 candidates hadn't been spectroscopically confirmed yet. That means no one had taken detailed spectra that would nail down the distances with certainty. They were educated guesses, very good educated guesses based on years of experience and sophisticated analysis techniques, but guesses nonetheless. Follow-up observations were scheduled. Webb's near-infrared spectrograph, an instrument that splits incoming light into its component wavelengths like a prism, was trained on the candidates one by one. Some of them were confirmed, their redshifts held. They really were as far away and as old as the initial estimates suggested. Others were revised downward. Their distances shrank. Their ages became less impossible. A few turned out to be something else entirely. Compact systems dominated not by stars, but by actively feeding black holes. These objects, which came to be nicknamed little red dots in later analyses, were bright because supermassive black holes at their centers were consuming matter at ferocious rates, heating the infalling gas to millions of degrees and producing enormous amounts of radiation. Not galaxies in the traditional sense, something weirder. But even after the most extreme candidates were walked back, the problem didn't go away. Webb was still finding more massive galaxies in the early universe than Lambda CDM comfortably predicted. Not just 1 or 2 outliers, entire populations of them. Every new deep field Webb observed seemed to contain early galaxies that were brighter and more structured than they had any right to be. And the sheer number of them made the statistical fluke explanation harder to defend. If you find one unusually massive galaxy in the early universe, you can call it a rare event, a lucky accident where conditions happened to be just right for rapid star formation. If you find dozens of them scattered across multiple independent fields of view, you have to start asking whether your models are missing something fundamental about how galaxies assemble. One of the key measurements astronomers use to understand early galaxies is their stellar mass, the total amount of matter locked up in stars. You can estimate stellar mass by looking at the galaxy's brightness in different wavelengths and comparing it to models of how stars of different ages and compositions emit light. Young, hot blue stars dominate the ultraviolet. Older, cooler red stars dominate the infrared. By measuring both and accounting for dust, which absorbs blue light and re-emits it as infrared, you can build a picture of the galaxy's stellar population and calculate how much total mass is sitting in stars. The problem is that for some of the early galaxies Webb has found, the stellar masses are enormous. Tens of billions of solar masses, in some cases approaching 100 billion, all packed into a galaxy seen when the universe was less than 1 billion years old. To put that in perspective, our Sun has been burning steadily for 4.6 billion years. It formed from a cloud of gas enriched by previous generations of stars, and it will live for another 5 billion before exhausting its hydrogen fuel. A galaxy containing 100 billion stars like the Sun would require a colossal amount of gas to form all those stars, and it would take billions of years for that gas to collapse, ignite, and settle into stable stellar orbits. Webb is finding galaxies that appear to have done that in a few 100 million years. The math doesn't work. Not under the standard assumptions about how fast stars can form and how efficiently gas can be converted into stars. Star formation efficiency is one of the key parameters in galaxy formation models. It measures what fraction of the available gas in a region actually ends up in stars. In the local universe, that efficiency is about 10%. For every kilogram of gas sitting in a molecular cloud, about 100 grams eventually collapse into a star. The rest gets blown away by stellar winds, radiation pressure, or supernova explosions, or it just drifts off and never participates in star formation at all. 10% is the baseline. In the early universe, when conditions were more chaotic and the first stars were more massive and more violent, the efficiency might have been even lower, maybe 5%, maybe less. But to build the massive early galaxies Webb is finding in the available time, you'd need efficiencies approaching 100%. Every atom of available gas would have to collapse into stars, with no waste, no gas blown away, no material left over. That doesn't happen, or at least it's not supposed to. Star formation is messy, it's inefficient. It's self-limiting because the first stars that form start blasting the surrounding gas with radiation and stellar winds, heating it up and making it harder for more stars to form. The process is supposed to regulate itself, preventing runaway star formation that would consume all available material in one go. These early galaxies appear to have skipped that step entirely, forming stars as fast as physically possible with no brake applied. One idea that's been floated to explain this is that the first generation of stars, those population 3 monsters, were even more efficient at forming than anyone realized. If the initial conditions in the early universe allowed molecular clouds to collapse much faster than they do today, you could compress the timeline significantly. Maybe instead of taking tens of millions of years for a cloud to collapse and form a cluster of stars, it took only a few million. Run that process over and over, and you could build up a large stellar population much faster than the standard models predict. The problem with this explanation is that we have no direct evidence for it. Population 3 stars have never been observed. They're a theoretical construct, inferred from the chemical composition of later generation stars and from models of how the first objects in the universe should have behaved. We know they must have existed because we see the heavy elements they created, but we've never actually seen one. And without seeing them, it's hard to test whether they really could have formed stars at the ferocious rates needed to explain Webb's observations. Another idea involves supermassive black holes. Some of the brightest early galaxies Webb has found appear to harbor black holes weighing millions of times the mass of the Sun sitting at their centers. Black holes that large take time to grow. A stellar mass black hole, the kind that forms when a massive star collapses, weighs maybe 10 or 20 solar masses. To get from 20 solar masses to 1 million solar masses, the black hole has to consume an enormous amount of material, and there are limits to how fast it can do that. When a black hole feeds, the infalling matter heats up and emits radiation. That radiation pushes back on the surrounding gas, creating pressure that resists further infall. The balance between the inward pull of gravity and the outward push of radiation is called the Eddington limit, and it sets a maximum rate at which a black hole can grow. Even feeding at that maximum rate, it takes hundreds of millions of years to grow a stellar mass black hole into a million solar mass monster. Finding million solar mass black holes in galaxies less than 1 billion years old creates the same timeline problem as the massive galaxies themselves. There simply hasn't been enough time for them to grow by conventional means. One solution is that these black holes didn't start small. Maybe they formed directly from the collapse of giant clouds of primordial gas, skipping the stellar phase entirely. These so-called direct collapse black holes could start out weighing tens of thousands or even hundreds of thousands of solar masses, giving them an enormous head start. From there, feeding at the Eddington limit, they could reach 1 million solar masses in the available time. The catch is that direct collapse black holes are purely theoretical. No one has ever observed one forming, and the conditions required for them to form are very specific. The gas cloud has to be massive, hot, and free of heavy elements that would allow it to cool and fragment into stars. Those conditions might have existed in the very early universe, but it's not clear how common they were. There's also the possibility that some of what Webb is seeing isn't stars at all. If a galaxy's light is dominated by an actively feeding supermassive black hole, the quasar at its core can outshine every star in the galaxy combined. From a distance, especially at the edge of the observable universe where resolution is limited, it can be hard to tell whether you're looking at a galaxy full of stars or a black hole surrounded by a glowing disk of superheated gas. Some of the little red dots that showed up in Webb's early data are probably examples of this. They're compact, they're extremely bright, and their spectra show features consistent with gas falling into a black hole rather than light from stars. If a significant fraction of the early massive galaxies Webb has found are actually black hole-dominated systems, that would relieve some of the pressure on star formation models. You wouldn't need to explain how to build 100 billion stars in a few 100 million years. You'd just need to explain how to grow a supermassive black hole that fast, which is still a problem, but a different problem. One of the more exotic explanations involves something called dark stars. Not black holes, actual stars, but powered by dark matter instead of nuclear fusion. The idea is that in the very early universe, when dark matter was much denser and more concentrated than it is today, particles of dark matter could have collided and annihilated inside the cores of the first protostars, releasing enormous amounts of energy. That energy would have heated the surrounding gas and caused the protostar to shine without needing fusion. A dark star powered by dark matter annihilation could potentially grow much larger and burn much brighter than a normal star, reaching masses of thousands or even millions of times the Sun. If dark stars existed in significant numbers in the early universe, they could explain the extreme brightness of some of the early galaxies Webb has found without requiring impossible star formation rates. It's a fascinating idea, but like most exotic explanations, it comes with caveats. Dark matter has never been directly detected. We infer its existence from gravitational effects, the way galaxies rotate, the way clusters of galaxies move, the way light bends around massive objects. But we don't know what dark matter is made of. We don't know how it interacts with itself or with ordinary matter beyond gravity. And we certainly don't know whether it can annihilate in the cores of stars and release energy. The dark star hypothesis requires a very specific type of dark matter, particles that are heavy enough and interactive enough to produce the necessary annihilation rates. Most dark matter candidates don't fit that profile. The leading candidate, something called a WIMP, a weakly interacting massive particle, is expected to interact so rarely that even in the dense core of a protostar, annihilation events would be far too infrequent to power a star. So dark stars, if they exist, would require a type of dark matter we haven't discovered yet. Another angle involves the timeline of reionization, the period when the first stars and galaxies began producing enough ultraviolet radiation to ionize the neutral hydrogen gas that filled the universe. Before reionization, the universe was opaque to certain wavelengths of light. After reionization, it became transparent, allowing light to travel freely across cosmic distances. The Standard Model places reionization somewhere between 200 million and 1 billion years after the Big Bang, a gradual process where pockets of ionized gas expanded and eventually merged into a fully ionized universe. Webb's early galaxies, if they're as massive and as bright as they appear, would have contributed significantly to reionization. In fact, they might have driven it much faster than the models predict. If reionization happened earlier and more rapidly than expected, it would change the timeline for when the first stars and galaxies could have formed. It would also change the conditions in the early universe, making it easier or harder for subsequent generations of galaxies to assemble, depending on how the ionizing radiation affected the surrounding gas. Some researchers have suggested that Webb's findings might require a complete rethinking of the reionization timeline, pushing the start earlier and compressing the entire process into a shorter window. That would have knock-on effects for almost everything else we think we know about the early universe, from the formation of the first black holes, to the chemical enrichment of intergalactic gas, to the development of the cosmic web. The uncomfortable truth is that every explanation for Webb's impossible galaxies requires either invoking new physics we haven't confirmed or stretching the existing physics to its absolute breaking point. You can make the Standard Model fit the data if you assume that star formation in the early universe was vastly more efficient than it is today. But that requires believing that conditions in the early universe were fundamentally different in ways we don't fully understand. You can explain the massive early black holes if you assume direct collapse black holes formed routinely. But that requires believing in a formation mechanism we've never observed. You can explain the extreme brightness if you assume dark stars existed. But that requires believing in a type of dark matter interaction we've never detected. Pick your poison. Every option comes with assumptions that aren't fully supported by independent evidence. What makes this particularly maddening for cosmologists is that the early universe is supposed to be simpler than the late universe. In the beginning, there were only hydrogen and helium, no heavy elements to complicate the chemistry. No dust to obscure the view, no complex feedback processes between stars and gas and black holes. The early universe was a blank slate, a laboratory where the fundamental processes of structure formation should have been easier to model and easier to understand. And yet Webb is showing us an early universe that's more complicated, more chaotic, and more efficient at building galaxies than anyone predicted. The blank slate turns out to have been covered in invisible writing. One of the most striking aspects of Webb's early galaxy discoveries is how quickly they appeared in the data. Hubble had spent decades staring at the distant universe, pushing the limits of its instruments to find the faintest, most distant objects it could detect. It found galaxies out to redshifts of about 11, corresponding to roughly 400 million years after the Big Bang. Those galaxies were dim, small, and exactly what the models predicted. They were proto-galaxies, the building blocks that would eventually merge and grow into the massive galaxies we see in the local universe today. Webb turned on and immediately found galaxies beyond Hubble's reach, galaxies at redshifts of 12, 13, even higher in some cases, and they weren't proto-galaxies. They were mature systems, bright and structured, sitting comfortably in a part of cosmic history where they shouldn't exist yet. The speed of the discoveries caught everyone off guard. Scientists expected Webb to find new things. That was the point. But they expected to find them gradually, after years of careful observation and analysis. Instead, the first deep field images released in July 2022 contained multiple candidate early galaxies that immediately challenged the standard model. By the end of Webb's first year of operations, the list of problematic objects had grown long enough that researchers were starting to talk seriously about whether Lambda CDM needed fundamental revisions, not tweaks, revisions. There's a phrase that keeps showing up in papers and conference talks about Webb's findings. The phrase is tension. The data are in tension with the models. Tension is a polite way of saying the observations don't match the predictions, but it's not quite strong enough to say the models are wrong. Tension implies that with some adjustments, some careful recalibrations, the two sides can be brought back into alignment. The question cosmologists are now asking is whether the tension around early galaxies is the kind that can be resolved with adjustments, or whether it's the kind that signals a deeper problem. The Hubble tension, the disagreement between two different methods of measuring the universe's expansion rate, has been simmering for years and hasn't gone away. The early galaxy tension is newer, but it's growing faster. Every new observation Webb makes seems to add another galaxy that's too massive, too bright, too well organized for its age. And unlike the Hubble tension, which involves a single number that two groups can't agree on, the early galaxy tension involves entire populations of objects spread across multiple redshifts and multiple regions of the sky. It's not one anomaly, it's a pattern, and patterns are much harder to dismiss than isolated outliers. If the early galaxies really are as massive and as mature as they appear, then something about our understanding of the first billion years of cosmic history is incomplete. Maybe the first stars formed faster than we thought. Maybe black holes grew faster. Maybe dark matter behaved differently in the early universe, clumping more aggressively and providing stronger gravitational wells for gas to fall into. Maybe the initial density fluctuations seeded by inflation were larger than the models predict, giving structure formation a head start. Or maybe the universe itself is older than we think, which would give everything more time to form. That last option is uncomfortable because we know the universe's age pretty precisely from the cosmic microwave background, from the oldest stars, from the decay rates of radioactive elements. There's not much room to add time without breaking other measurements. The early galaxies Webb has found are ghosts in a very specific sense. They're light from objects that no longer exist in the form we're seeing them. The galaxies we're observing at redshift 13 existed 13 billion years ago. Today, if they still exist, they've merged with other galaxies, evolved, changed beyond recognition. We're seeing their ancient light, fossils preserved in the spectrum, and those fossils are telling us that the universe was doing things we didn't expect, building faster, organizing sooner, creating complexity in a window of time that was supposed to be too short for complexity to emerge. The ghosts are challenging the timeline, and if the timeline is wrong, then everything built on top of it, every model of how galaxies form, how stars evolve, how black holes grow, all of it needs to be reconsidered. The discoveries aren't slowing down. Webb is still observing, still finding new objects at the edge of the observable universe, still pushing the boundaries of what we thought was possible. And while astronomers struggle to explain galaxies that assembled too quickly in the early universe, another crisis is deepening closer to home. A crisis that doesn't involve distant galaxies or ancient light, but the most fundamental measurement in cosmology: the rate at which space itself is expanding. Because the universe, it turns out, is not just assembling itself faster than expected, it's also flying apart faster than the models predict. And the two problems, the too fast galaxies and the too fast expansion, might be connected in ways no one has figured out yet. The discoveries aren't slowing down. Webb is still observing, still finding new objects at the edge of the observable universe, still pushing the boundaries of what we thought was possible. And while astronomers struggle to explain galaxies that assembled too quickly in the early universe, another crisis is deepening closer to home. A crisis that doesn't involve distant galaxies or ancient light, but the most fundamental measurement in cosmology: the rate at which space itself is expanding. Because the universe, it turns out, is not just assembling itself faster than expected. It's also flying apart faster than the models predict. And the two problems, the too fast galaxies and the too fast expansion, might be connected in ways no one has figured out yet. The crisis has a name. Cosmologists call it the Hubble tension, and it's been quietly gnawing at the foundations of the field for nearly a decade. The tension is simple to describe, but extraordinarily difficult to resolve. Two different methods of measuring how fast the universe is expanding give two different answers. Not slightly different, different enough that the odds of it being a statistical fluke are vanishingly small. One method looks at the universe today, measuring distances to nearby galaxies and calculating how fast they're receding. The other method looks at the universe as it was nearly 14 billion years ago, analyzing the faint glow of radiation left over from the Big Bang and using the standard cosmological model to predict what the expansion rate should be today. Both methods are sophisticated. Both have been refined and tested for years. Both are backed by teams of brilliant scientists who have checked and rechecked their work. And they disagree by about 10%. 10% doesn't sound like much. If you ordered a pizza and got 10% less pepperoni than you expected, you'd probably shrug and eat it anyway. But in cosmology, where measurements are routinely precise to within 1 or 2%, a 10% disagreement is enormous. It's the difference between a universe that's roughly 13.8 billion years old and one that could be a billion years younger. It changes the distances between galaxy clusters. It affects the amount of dark energy driving the universe's accelerating expansion. It shifts the timeline for when the first stars ignited and when galaxies began to form. 10% is not a rounding error. It's a crack running through the middle of the standard model. Let's start with how the two measurements work, because understanding why they disagree requires understanding what they're actually measuring. The first method, the one that looks at the universe today, is called the cosmic distance ladder. It's a step-by-step process that builds up a map of distances to farther and farther objects, using each rung of the ladder to calibrate the next. The ladder starts close to home with parallax, the apparent shift in a star's position as Earth orbits the Sun. Parallax only works for stars within a few hundred light-years, so once you've mapped those, you move to the next rung. Cepheid variable stars, which are stars whose brightness pulses at a rate directly tied to how luminous they actually are. Measure the pulse, calculate the true brightness, compare it to how bright the star looks from Earth, and you've got a distance. Cepheids can be spotted in galaxies millions of light-years away, so they extend the ladder much farther. The next rung uses Type Ia supernovae, exploding white dwarf stars that all detonate with roughly the same peak brightness. Once you've calibrated them with Cepheids in the same galaxy, you can spot them in galaxies hundreds of millions of light-years away and calculate how far those galaxies are. Combine those distances with measurements of how fast the galaxies are moving away from us, which you get from the redshift of their light, and you can calculate the Hubble constant, the rate at which the universe is expanding right now. The team leading this effort is called SH0ES, which stands for Supernova H0 equation of state. The H0 is the symbol for the Hubble constant. The team is led by Adam Rees, a Nobel Prize-winning physicist at Johns Hopkins University, who shared the prize in 2011 for discovering that the universe's expansion is accelerating. Rees and his colleagues have spent years refining the distance ladder using the Hubble Space Telescope and now the James Webb Space Telescope to measure Cepheids with unprecedented precision. Their most recent result, published in late 2024, gives a Hubble constant of about 73 kilometers per second per megaparsec. A megaparsec is roughly 3.26 million light-years. So for every 3.26 million light-years you look outward into space, galaxies are moving away from us 73 kilometers per second faster. The second method doesn't use ladders or supernovae or any direct measurements of distances in the local universe. It looks backward, all the way to the cosmic microwave background, the faint glow of radiation that fills the entire sky. This radiation was emitted about 380,000 years after the Big Bang, when the universe cooled enough for hydrogen atoms to form and light could finally travel freely through space. The cosmic microwave background is the oldest light in the universe, and it contains an enormous amount of information about what the universe was like back then. Tiny fluctuations in the temperature of the radiation, variations of only a few millionths of a degree, map out the distribution of matter and energy in the early universe. Those fluctuations are the seeds of everything that came later. Galaxies, clusters, the entire cosmic web, all of it grew from those tiny ripples. The European Space Agency's Planck satellite spent about 4.5 years mapping the cosmic microwave background in exquisite detail. From that map, physicists extracted the conditions of the early universe: how much ordinary matter there was, how much dark matter, how much dark energy, how fast the universe was expanding back then, all encoded in the pattern of hot and cold spots in the radiation. Then they took those numbers and plugged them into the equations of the standard cosmological model, lambda CDM, and ran the clock forward nearly 14 billion years to predict what the expansion rate should be today. The answer they got was about 67 kilometers per second per megaparsec. Not 73, 67. That 6 kilometer per second difference is the Hubble tension. It's been confirmed by multiple independent teams using different data sets and different analysis techniques. It's not going away, and it's not getting smaller. If anything, as the measurements have gotten more precise over the past decade, the tension has gotten worse. Early on, when the error bars were larger, you could argue that the two measurements overlapped within their uncertainties and the disagreement was just noise. Not anymore. The uncertainties have shrunk. The two values are now separated by more than 5 standard deviations, which in statistics is the threshold for claiming a discovery. 5 sigma is the gold standard. It's what physicists required before announcing the detection of the Higgs boson. A 5 sigma discrepancy between two measurements means the odds that it's a random fluke are less than 1 in a million. Something is wrong. Either one of the measurements has a systematic error no one has found, or the standard model is incomplete. Adam Rees, in interviews and conference talks, has been blunt about the implications. In 2019, at a meeting at the Kavli Institute for Theoretical Physics in California, he asked David Gross, a Nobel laureate in particle physics, whether the field should start calling this a problem. Gross told him no. They should call it a crisis. That word, crisis, is not used lightly in physics. It's what you call a situation where the observational evidence is strong enough and consistent enough that ignoring it is no longer an option. The Hubble tension is a crisis because after nearly a decade of checking and rechecking, neither measurement shows any sign of budging, and the longer the disagreement persists, the harder it becomes to believe that it's just a mistake. So what could explain it? There are essentially three possibilities, and none of them are comfortable. The first is that one of the measurements has a systematic error that hasn't been identified yet. Systematic errors are the sneaky kind. They're not random noise that averages out when you collect more data. They're consistent biases that shift all your measurements in the same direction, and they can be incredibly hard to spot because they're often buried in the assumptions you make when analyzing the data. For the local measurement, the cosmic distance ladder, the most obvious place to look for systematic errors is in the calibration of Cepheid variable stars. Cepheids live in crowded regions of galaxies, often surrounded by other stars and clouds of dust. If the light from nearby stars blends together with the Cepheid's light, the Cepheid will appear brighter than it actually is. Brighter means you calculate a shorter distance. Shorter distances mean a higher Hubble constant. This was the leading explanation for the tension for several years. Many astronomers assumed that once someone pointed a sharper telescope at the Cepheids and resolved the blending, the tension would relax and the Hubble constant would drop back towards 67. That's one of the main reasons Adam Rees's team pushed so hard to get observing time on the James Webb Space Telescope. Webb's infrared cameras can cut through dust and resolve individual stars in distant galaxies with a clarity Hubble can't match. If blending was the problem, Webb would reveal it. The Cepheids would look dimmer through Webb's eyes. The distances would stretch. The Hubble constant would drop. Crisis averted. Webb's first results came back in early 2023. The Cepheids looked the same. The distances held. The Hubble constant stayed at 73. By late 2024, Rees's team had published their largest Webb study yet, covering more than 1,000 Cepheids across 5 host galaxies. They used 3 independent methods to cross-check the distances, including a technique called the tip of the red giant branch that doesn't rely on Cepheids at all. All 3 methods agreed. The local measurement was solid. Blending wasn't the problem. Systematic errors in the distance ladder, if they exist, are well hidden enough that the most powerful telescope ever built couldn't find them. What about the other measurement, the one based on the cosmic microwave background? Could there be systematic errors hiding there? It's harder to see where they'd come from. The cosmic microwave background is one of the most precisely measured quantities in all of science. Planck's map of the radiation has been analyzed by dozens of independent teams, and they all get the same answer. The pattern of fluctuations matches the predictions of lambda CDM almost perfectly. The model fits the data so well that cosmologists have nicknamed it the concordance model, because everything agrees. The age of the universe, the density of matter, the amount of dark energy, the distribution of galaxies, all of it lines up. Except for the Hubble constant, that one number refuses to cooperate. If systematic errors can't explain the tension, then the second possibility is that the standard model is missing something. Some piece of physics that affects how the universe expands but hasn't been accounted for in the equations. One idea that's gotten a lot of attention is called early dark energy. Dark energy is the mysterious force that's been accelerating the universe's expansion for the past 5 billion years or so. It's usually modeled as a constant, a fixed amount of energy density that stays the same everywhere in space and at all times. But what if it's not constant? What if there was an extra burst of dark energy in the very early universe, a temporary boost that gave the expansion a kick right after the Big Bang and then faded away? If something like that happened, it would change the conditions in the early universe just enough to shift the predicted Hubble constant upward, closer to the 73 that the local measurements give. Early dark energy is an elegant idea because it solves the Hubble tension without breaking everything else that lambda CDM gets right. The cosmic microwave background would still look the same. The distribution of galaxies would still match observations. You just need to add one extra parameter to the model, a brief phase of accelerated expansion that occurred before the cosmic microwave background was emitted. The problem is that early dark energy is entirely hypothetical. No one has detected it. No one knows what would cause it. And adding extra parameters to a model is something physicists try to avoid unless absolutely necessary. The whole point of the standard model is that it explains an enormous range of observations with just 6 parameters. Start adding more, and you risk turning the model into a patchwork of ad hoc fixes that fit the data but don't actually explain anything. Another possibility points to something wrong with our understanding of dark matter. Dark matter is the invisible scaffolding that holds galaxies and clusters together. It doesn't emit light, doesn't absorb light, doesn't interact with ordinary matter except through gravity. We infer its existence from the way galaxies rotate, the way clusters move, the way light bends around massive objects. Lambda CDM assumes dark matter is cold, meaning it moves slowly compared to the speed of light, and that it's distributed fairly evenly across the universe. But what if dark matter behaved differently in the early universe than it does today? What if it clumped together more aggressively or interacted with itself in ways we haven't accounted for? Changes to how dark matter behaves could affect the rate at which structures formed, which could in turn affect the expansion rate in ways that shift the predicted Hubble constant. This is speculative territory. We don't know what dark matter is made of. We don't know how it interacts with itself. We've never directly detected a dark matter particle despite decades of experiments trying. So proposing that dark matter behaves differently than we thought is a bit like solving one mystery by invoking another mystery. It might be true, but it doesn't give you much to work with. The third possibility, the one that keeps surfacing in conversations about the Hubble tension, is that general relativity itself might need modification at the largest scales. General relativity has been tested extensively in the solar system, around black holes, in neutron-star mergers, and it works beautifully. But cosmology pushes the theory to scales it's never been tested at before, distances of billions of light-years, timescales of billions of years, enormous amounts of dark matter and dark energy that we can't see or touch. It's possible that general relativity, as elegant and successful as it is, breaks down slightly at those scales in ways that change how we calculate the expansion rate. Modified gravity theories have been proposed, tweaks to Einstein's equations that behave like standard general relativity in most situations but deviate slightly when applied to the entire universe. Some of these theories can adjust the predicted Hubble constant without destroying the rest of the model. The catch is that they tend to make other predictions that don't match observations, or they introduce new parameters that make the theory more complicated without obviously improving it. So where does the James Webb Space Telescope fit into all of this? Webb wasn't designed to measure the Hubble constant directly. It's not a tool for solving the Hubble tension, but the data it's been collecting, especially the discoveries of massive galaxies in the early universe, are starting to complicate the picture in ways no one fully anticipated. Here's why. The cosmic microwave background measurement of the Hubble constant relies on a specific model of how the universe evolved from the time the radiation was emitted to today. That model makes assumptions about how quickly structures formed, how efficiently gas turned into stars, how much dust and heavy elements were present at different times. If those assumptions are wrong, the predicted expansion rate could be off. Webb is finding galaxies at redshifts of 10, 12, 13, seen as they existed just a few 100 million years after the Big Bang. And those galaxies are more massive, more luminous, and more mature than the standard model predicts they should be at that stage of cosmic history. If the early universe was building galaxies faster and more efficiently than the models assume, then other things about the early universe might also be different. The rate of star formation, the amount of dust, the distribution of dark matter, the timing of reionization. All of those factors feed into the models that predict what the Hubble constant should be based on the cosmic microwave background. Change the inputs even slightly, and the output shifts. It's not a direct connection. Webb's early galaxies don't tell you how fast the universe is expanding today, but they do tell you that the standard assumptions about the early universe might be incomplete. And if those assumptions are incomplete, then the Hubble constant derived from the cosmic microwave background might not be as reliable as everyone thought. That doesn't mean the local measurement is automatically right. It just means the cosmic microwave background measurement might be missing something important. One of the key parameters that connects early galaxy formation to the Hubble tension is something called the star formation efficiency. This measures what fraction of the available gas in a region of space actually collapses into stars. In the local universe, that efficiency is about 10%. In the early universe, the standard models assume it was similar, maybe even lower because conditions were more chaotic and the first stars were more violent. But to explain the massive galaxies Webb is finding, you'd need efficiencies much higher, approaching 50 or even 100% in some cases. If star formation really was that efficient in the early universe, it would change the amount of light and energy being produced at those early times, which would affect the ionization state of the gas, which would affect how structures formed, which could eventually feed back into the predicted expansion rate. It's a complicated chain of reasoning, and no one has worked out all the details yet. But the basic point is that Webb's discoveries are adding new constraints to the models, and those constraints are making it harder to fit everything together consistently. Before Webb, cosmologists could tune the models to match the cosmic microwave background and get a Hubble constant of 67. And everything seemed fine. Now Webb is saying the early universe was doing things the models didn't predict, which means the models need adjustment. But adjusting the models to fit Webb's data might shift the predicted Hubble constant in ways that make the tension worse, not better. There's also the possibility that Webb's early galaxies are telling us something about dark energy. If dark energy was stronger in the early universe, or if it varied over time rather than being constant, it could have affected how quickly the universe expanded during the period when the first galaxies were forming. A stronger early expansion would make it harder for gravity to pull matter together, which would slow down galaxy formation. But Webb is finding the opposite. Galaxies are forming faster than expected. So if dark energy is involved, it would have to be behaving in a way that somehow made structure formation more efficient, not less. No one has a good explanation for how that would work. Another angle involves black holes. Some of the brightest objects Webb has found in the early universe appear to be powered by supermassive black holes, not stars. Black holes weighing millions of times the mass of the Sun, feeding on gas and producing enormous amounts of radiation. If those black holes formed earlier and grew faster than the models predict, they could have ionized the surrounding gas more rapidly, changing the conditions for galaxy formation and potentially affecting the expansion rate indirectly through feedback processes that aren't fully understood. Again, this is speculative. The connection between early black hole growth and the Hubble constant isn't direct. But the fact that Webb is finding so many things that don't fit the standard timeline suggests that the timeline itself might need rethinking. One of the researchers working on the Hubble tension, A cosmologist named Wendy Friedman at the University of Chicago has been building her own version of the distance ladder that relies less heavily on CFIDs. Her team uses red giant stars and a class called JWST stars, which are found in less crowded regions of galaxies and are less affected by dust and blending. When she analyzed Webb data in mid-2024, her results landed somewhere in the middle, not 73, not 67, around 70. Her conclusion was that the tension might not be as severe as the two extreme measurements suggest, and that more work is needed to figure out which method is actually right. That didn't resolve the crisis, it just added another layer of uncertainty. The most honest assessment anyone can give right now is that the Hubble tension remains unsolved. The local measurements keep giving 73. The cosmic microwave background keeps giving 67. Webb's discoveries of impossible early galaxies are adding complications that might eventually help explain the discrepancy, but for now they're mostly just making the whole picture messier. And the longer the tension persists, the harder it becomes to believe that it's just a mistake waiting to be corrected. Something about our understanding of how the universe expands, or how it evolved, or how we're measuring it, is incomplete. Adam Rees, who has spent his career measuring the expansion rate with ever-increasing precision, summed it up plainly. With the errors eliminated, what's left is the possibility that we have misunderstood the universe. That's not the kind of statement a Nobel Prize-winning physicist makes lightly. It's what you say when the data has backed you into a corner and every conventional explanation has been ruled out. The Hubble tension is telling cosmologists that something fundamental is wrong. Either the distance ladder is systematically biased in a way no one has been able to identify, or the cosmic microwave background analysis is missing a crucial piece of physics, or the standard model itself is incomplete. Pick your option. None of them are comfortable. The frustrating part is that cosmology has never been more precise. The measurements have never been sharper, the data have never been cleaner. And yet the most basic number in the field, the rate at which the universe is expanding, remains a matter of dispute. The Hubble constant should be one number. It should be knowable. It should be something every measurement converges on as the instruments get better. Instead, the measurements are diverging. The local value is going up slightly as the data improve. The cosmic microwave background value is staying rock solid, and the gap between them is widening. Webb's role in all of this is indirect but important. It's not solving the Hubble tension, but it's expanding the list of things that don't fit, and every new anomaly makes it harder to pretend the standard model is complete. The early massive galaxies, the oversized black holes, the unexpectedly bright systems at extreme redshifts, all of it points in the same direction. The universe assembled itself faster and more efficiently than lambda CDM predicts. If the early universe was different, if structure formation happened differently, if the assumptions baked into the cosmic microwave background analysis are wrong, then the predicted Hubble constant might be wrong too. And if the predicted value is wrong, then the local measurement, the 73, might be the one that's actually correct. The universe might really be expanding 10% faster than the standard model says it should. That possibility is both exciting and terrifying. Exciting because it would mean new physics, something unexpected and unexplained that could open up entirely new areas of research. Terrifying because it would mean rethinking almost everything cosmologists have built over the past century, the age of the universe, the timeline of structure formation, the nature of dark energy, the behavior of dark matter. All of it would need to be revisited. And there's no guarantee that the new picture, whatever it turns out to be, will be any simpler or more elegant than the old one. Science doesn't owe us simplicity. The universe is under no obligation to make our equations easy to solve. The Hubble tension is not going away. The James Webb Space Telescope is not going to solve it by itself, but it's adding pressure. Every impossible galaxy, every too-old star, every black hole that shouldn't exist yet, all of it is building a case that the standard model is missing something. And the more the evidence piles up, the harder it becomes to keep patching the cracks with minor adjustments and hoping the structure holds. At some point, you have to step back and ask whether the foundation itself is sound, whether the rules cosmologists have been using for the past century are still the right rules, whether the universe is telling us loudly and consistently that it's time to rewrite the playbook. The Hubble tension is not going away. The James Webb Space Telescope is not going to solve it by itself, but it's adding pressure. Every impossible galaxy, every too-old star, every black hole that shouldn't exist yet, all of it is building a case that the standard model is missing something. And the more the evidence piles up, the harder it becomes to keep patching the cracks with minor adjustments and hoping the structure holds. At some point, you have to step back and ask whether the foundation itself is sound, whether the rules cosmologists have been using for the past century are still the right rules, whether the universe is telling us loudly and consistently that it's time to rewrite the playbook. Let's take a step back and look at what we've accumulated, not individual anomalies anymore, a pattern. The Big Ring sits in the data at 1.3 billion light-years across, violating the cosmological principle's prediction that the universe should be smooth on scales larger than a few 100 million light-years. The giant arc stretches 3.3 billion light-years, nearly 3 times the theoretical maximum size for structures that should have had time to form in a universe only 13.8 billion years old. Webb found galaxies at redshifts of 10, 12, 13, seen as they existed just a few 100 million years after the Big Bang. Galaxies that are too massive, too bright, too organized for an infant cosmos. Supermassive black holes weighing millions of times the mass of the Sun are sitting in those galaxies when they should have needed billions of years to grow that large. And the Hubble constant, the single number that describes how fast the universe is expanding right now, gives 2 different answers depending on how you measure it. 73 if you look at the local universe, 67 if you extrapolate forward from the cosmic microwave background. Each one of these findings, taken alone, could be explained, maybe explained away. A statistical fluke here, a measurement error there, an overlooked detail in the modeling. But taken together, they're not flukes, they're a chorus. And what they're singing is that something fundamental about the standard cosmological model, lambda CDM, the framework that has guided the field for decades, is incomplete. Not entirely wrong. The model still explains an enormous range of observations with remarkable precision. The cosmic microwave background, the distribution of galaxies, the abundance of light elements, the accelerating expansion, all of it fits, but the edges are fraying. The parts of the model that describe how structures form, how fast they form, and how large they can grow, those parts are under strain, and the strain is starting to show in ways that can't be ignored anymore. The cosmological principle, the assumption that the universe is homogeneous and isotropic on large scales, has been a cornerstone of cosmology since the 1920s. It's what allows cosmologists to describe the entire universe with a single set of equations. Without it, you'd need different equations for every region of space, and the whole project of modeling the cosmos would become intractable. The principle isn't just convenient, it's necessary for the math to work. But the Big Ring and the giant arc are direct violations of that principle. They're structures that are too large, too organized, sitting at scales where the universe is supposed to have smoothed out into uniformity. If the cosmological principle breaks down at scales of 1 billion light-years or more, then every prediction built on top of it needs to be reconsidered. The Hubble constant, the age of the universe, the timeline of structure formation, the amount of dark matter and dark energy, all of it gets called into question. One possibility that keeps surfacing in theoretical discussions is that the cosmological principle is approximately correct, but not perfectly correct. Maybe the universe doesn't become truly homogeneous until you average over scales much larger than anyone expected. Not 1 billion light-years, maybe 5 billion, maybe 10. If that's the case, then the Big Ring and the giant arc are just unusually large members of the hierarchy of cosmic structure. And if we mapped more of the universe, we'd eventually find that things do smooth out, just at a scale we haven't reached yet. That explanation has the advantage of not requiring any new physics. It just requires accepting that the scale of homogeneity is bigger than we thought. The downside is that it makes cosmology harder. If the universe isn't homogeneous on the scales we've been modeling, then all the equations that rely on that assumption, the Friedmann equations that describe the universe's expansion, need to be applied more carefully. You can't just plug in a single value for the density of matter and call it a day. You have to account for local variations, and those variations propagate through the calculations in complicated ways. Another idea that's gained traction is called modified gravity. General relativity has been tested extensively in the solar system, around black holes, in neutron star mergers, and it works beautifully. But cosmology pushes the theory into regimes it's never been tested before. Distances of billions of light-years, timescales of billions of years, enormous concentrations of dark matter and dark energy that we can't observe directly. It's possible that Einstein's equations, as elegant and successful as they are, need slight modifications when applied to the universe as a whole. Modified gravity theories tweak the relationship between matter, space, and time in ways that leave most of general relativity intact, but change how gravity behaves on very large scales or in very weak gravitational fields. One version of modified gravity, called MOND, which stands for Modified Newtonian Dynamics, was originally proposed to explain why galaxies rotate faster than they should based on the visible matter they contain. MOND adjusts Newton's laws of motion so that in regions where gravity is extremely weak, objects experience slightly more gravitational pull than Newton or Einstein would predict. The idea was that if you tweaked gravity just right, you wouldn't need dark matter to explain galactic rotation curves. The problem is that MOND doesn't work for everything. It can explain some galactic dynamics, but it fails spectacularly when applied to galaxy clusters or the cosmic microwave background, and it doesn't make useful predictions about large-scale structure formation. Most cosmologists consider MOND a dead end, an interesting idea that doesn't fit enough of the data to be taken seriously. But the broader concept, that gravity might behave differently on cosmic scales, hasn't gone away. There are more sophisticated versions of modified gravity that keep general relativity intact in most situations, but introduce small deviations when you're dealing with the entire universe. These theories often involve extra fields or dimensions, mathematical constructs that don't correspond to anything we can see or measure directly, but that change the equations in ways that could potentially resolve some of the tensions cosmology is facing. The challenge with modified gravity is that every version proposed so far either makes predictions that don't match observations or introduces so many free parameters that the theory loses its predictive power. You can always fit the data if you're allowed to adjust enough knobs. The question is whether the theory explains anything or just describes it. Then there's dark energy, the mysterious force driving the universe's accelerated expansion. Lambda CDM treats dark energy as a cosmological constant, a fixed energy density that permeates all of space and doesn't change over time. The constant is represented by the Greek letter lambda, which is where the model gets its name. A cosmological constant is mathematically simple and fits the data well, but it's also deeply unsatisfying because no one has a good explanation for why it has the value it does. The observed value of the cosmological constant is so small that it's almost zero, but not quite. If it were actually zero, the universe wouldn't be accelerating. If it were much larger, the universe would have expanded so fast that galaxies never would have formed. The value we measure is sitting in a very narrow range that allows structure to exist, and that fine-tuning makes physicists uncomfortable. One alternative is that dark energy isn't constant. Maybe it changes over time or varies from place to place. This idea goes by several names depending on the details, but one version that's gotten attention is called phantom dark energy. In this model, dark energy gets stronger as the universe expands, eventually overwhelming gravity so completely that it tears apart galaxies, stars, even atoms in what's called a big rip. Phantom dark energy is mostly theoretical and doesn't have strong observational support, but it's one of the few ideas that could explain why the universe seems to be expanding faster than the cosmic microwave background predicts. If dark energy was weaker in the early universe and has been getting stronger over time, the predicted expansion rate based on early universe observations would be too low. The local measurements, which reflect the current strength of dark energy, would give a higher value. That matches the pattern of the Hubble tension. The trouble with phantom dark energy, like most exotic explanations, is that it requires introducing new physics we have no independent evidence for. It's solving one mystery by invoking another mystery. That's not automatically wrong. Science does that all the time. Dark matter itself is an unseen, undetected substance invoked to explain gravitational effects we can't otherwise account for. The difference is that dark matter has multiple independent lines of evidence pointing to its existence. Galaxy rotation curves, gravitational lensing, the cosmic microwave background, the distribution of galaxy clusters, all of them require dark matter or something very much like it. Phantom dark energy, by contrast, is mostly motivated by the Hubble tension. If the tension turned out to be a measurement error after all, the case for phantom dark energy would collapse. That makes it a risky bet. Another angle involves primordial fluctuations, the tiny density variations in the very early universe that seeded all the structure we see today. Those fluctuations are thought to have been generated during inflation, a brief period of exponential expansion in the first fraction of a second after the Big Bang. Inflation stretched quantum fluctuations to cosmic scales, and those fluctuations later grew under gravity into galaxies, clusters, and the cosmic web. The standard model assumes those initial fluctuations followed a specific statistical pattern, a nearly scale-invariant spectrum that's been measured precisely from the cosmic microwave background. But what if the spectrum isn't quite what we think? What if there were larger fluctuations on very large scales, or smaller fluctuations on very small scales, that the cosmic microwave background didn't fully capture? That could change how quickly structures formed and how large they could grow, potentially explaining both the oversized structures Lopez found and the early massive galaxies Webb detected. The difficulty is that inflation itself is still a hypothesis. It explains the cosmic microwave background beautifully, and it's the leading theory for what happened in the first moments after the Big Bang, but it's never been directly confirmed. We don't know what field drove inflation. We don't know how long it lasted. We don't know whether it happened once or multiple times. And there are dozens of different versions of inflation, each making slightly different predictions about the initial fluctuations. Some versions allow for larger fluctuations on large scales. Others predict deviations from scale invariance that could affect structure formation. But without direct evidence of inflation, without some smoking gun signature that definitively proves the theory, it's hard to use it as a foundation for solving other mysteries. You're stacking one uncertain theory on top of another and hoping the whole structure doesn't collapse. What's becoming increasingly clear is that the standard model, lambda CDM, is not going to be thrown out. It's too successful. It explains too much, but it's almost certainly going to be modified, extended. The question is, what kind of modification will work? Does the cosmological principle need a softer formulation that allows for larger structures? Does dark energy need to be dynamic instead of constant? Does gravity need adjustment at cosmic scales? Do the initial conditions from inflation need revision? Or is it some combination of all of the above, a series of small tweaks that together shift the predictions just enough to bring them into line with Webb's discoveries and the local measurements of the Hubble constant? The frustrating part is that we won't know until we have more data, and getting more data takes time. Webb is still observing. It's only been operational for a little over 2 years as of late 2024, and it's expected to keep running for at least another decade, possibly longer if the fuel and instruments hold out. Every additional year of observations will add more galaxies to the census, more measurements of the early universe, more constraints on how structures formed and when. The European Space Agency is planning a mission called Euclid, a space telescope designed to map the distribution of galaxies across billions of light-years with unprecedented precision. Euclid launched in mid-2023 and is beginning to return data. Its goal is to measure the geometry of the universe and the behavior of dark energy by mapping how galaxies cluster and how light from distant objects is bent by intervening matter. If dark energy is changing over time, Euclid should be able to detect it. NASA is also planning a mission called the Nancy Grace Roman Space Telescope, named after one of the first female executives at NASA who played a key role in planning the Hubble Space Telescope. Roman is designed to have a field of view 100 times larger than Hubble's while maintaining similar resolution. It will survey enormous areas of the sky, finding thousands of supernovae, mapping the structure of the Milky Way, and searching for exoplanets. Roman's supernova survey, in particular, is expected to provide new measurements of the Hubble constant that could help resolve the tension. If the distance ladder measurements are correct, Roman should confirm them. If there's a systematic error hiding in the current data, Roman's larger sample size and different observing strategy should reveal it. Roman is scheduled to launch in the mid-2020s, assuming no further delays. On the ground, next-generation telescopes are being built that will dwarf anything currently operational. The Extremely Large Telescope, or ELT, is under construction in Chile. When completed, it will have a primary mirror 39 meters across, making it the largest optical telescope ever built. The ELT will be able to observe the atmospheres of exoplanets, study the formation of the first stars and galaxies, and map the distribution of dark matter with a precision that current ground-based telescopes can't match. The 30-meter telescope, or TMT, is planned for Hawaii, though construction has been delayed by local opposition. If it gets built, it will be similarly powerful, and the Giant Magellan Telescope, or GMT, is being constructed in Chile with a segmented mirror that will have an effective diameter of 24.5 meters. All three of these telescopes are expected to come online in the late 2020s or early 2030s, and together they'll provide a massive leap in observational capability. What will those telescopes find? No one knows. That's the exciting part, and the terrifying part. If the anomalies Webb has found are real, If the Big Ring and the giant arc and the early massive galaxies are telling us that the standard model is incomplete, then the next generation of telescopes will almost certainly find more anomalies, bigger structures, older galaxies, faster expansion rates. Each new discovery will tighten the constraints on what kind of new physics is needed to explain everything. But it's also possible that the next wave of data will resolve the tensions in unexpected ways. Maybe the Hubble tension will turn out to be a subtle calibration issue that no one has found yet. Maybe the Big Ring and the giant arc will turn out to be projection effects after all, chance alignments that look more significant than they are. Maybe the early massive galaxies will be explained by a slight adjustment to star formation efficiency that doesn't require rethinking the entire timeline of cosmic history. The honest answer is that we're in a period of uncertainty, and uncertainty is uncomfortable. Scientists like to have answers, definitive answers backed by solid data and rigorous theory. But cosmology, especially observational cosmology, doesn't always cooperate. The universe doesn't hand you answers on a silver platter. It hands you puzzles, and sometimes the puzzles take decades to solve. The cosmological constant, the idea that empty space has energy, was proposed by Einstein in 1917, dismissed as his biggest blunder, and then resurrected in the late 1990s when observations of distant supernovae showed that the universe's expansion is accelerating. It took 80 years for that puzzle to resolve, and even now, we don't fully understand what dark energy is or why it has the value it does. The Hubble tension has been simmering for less than a decade. The Big Ring was announced in early 2024. Webb's first observations of impossible galaxies came in mid-2022. These are brand new problems. Cosmology moves slowly. We might not have satisfying answers for another 10 years, maybe longer, but that's how science works. Progress isn't linear. It's not a steady march from ignorance to knowledge. It's a messy, chaotic process where observations force you to reconsider assumptions you thought were solid, where elegant theories get complicated by inconvenient data, where the more you learn, the more you realize you don't know. And that's okay. That's the point. Science isn't about having all the answers. It's about asking better questions. And right now, cosmology is being forced to ask some very hard questions. Do we need a new standard model? That's the question Alexia Lopez posed after discovering the Big Ring and the giant arc. It's the question Adam Rees has been circling around as the Hubble tension refuses to go away. It's the question implied by every impossible galaxy Webb finds in the early universe. And it's a question no one can answer yet. Lambda CDM is not going to be thrown out overnight. Too much of it works too well. But it's almost certainly going to be extended, refined, made more complicated in order to fit the data. Whether that extension will involve new fields, new forces, new particles, or just a more careful accounting of the physics we already know, that's still an open question. There's also a philosophical dimension to all of this that's worth pausing on. The anomalies Webb has found, the structures that shouldn't exist, the galaxies that formed too fast, the expansion rate that won't settle on a single value. All of it is a reminder that the universe doesn't care about our models. It doesn't care whether our equations are elegant or our theories are simple. It is what it is. And our job as scientists is to figure out what that is, even when it turns out to be stranger and more complicated than we expected. The history of physics is full of moments where the universe forced scientists to abandon ideas they were deeply attached to. The Earth isn't the center of the solar system. Time and space aren't absolute. The universe had a beginning. Each of those realizations was uncomfortable. Each one required rethinking foundational assumptions, and each one led to a deeper, more accurate understanding of reality. We might be at one of those moments now. The standard model of cosmology has been extraordinarily successful for decades. It's guided research, made predictions, explained observations, but it's showing cracks. And when a model starts showing cracks, you have two choices. You can try to patch them and hope the structure holds, or you can step back, acknowledge that the cracks are telling you something important, and start building a better model. Cosmology is at that crossroads. The patches are getting harder to apply, the anomalies are piling up too fast, and the evidence is pointing, more and more insistently, toward the need for something new. What that something is, no one knows yet. It might be a modification to how gravity works at the largest scales. It might be a better understanding of dark energy and how it evolves over time. It might be a revision to the initial conditions set during inflation. It might be something no one has thought of yet because the data haven't been precise enough until now to point the way. But whatever it is, it's going to emerge from the observations, from Webb's deep fields, from the Sloan survey's maps of large-scale structure, from the next generation of telescopes that will come online in the next decade. The universe is telling us something. It's been telling us for a while now. The challenge is listening carefully enough to figure out what it's trying to say. The big ring sits in the data at 1.3 billion light-years across. The giant arc stretches 3.3 billion light-years. Webb found galaxies at the edge of time, massive and bright and organized when they should have been small and dim and chaotic. The Hubble constant refuses to be one number. And every time scientists think they've found an explanation, the next observation complicates it. These aren't minor issues. They're not rounding errors or statistical flukes. They're signals that the playbook needs rewriting, not because the old playbook was wrong, but because it was incomplete. It got us this far. It explained what we could see with the telescopes we had, but now we have better telescopes. And the better telescopes are showing us a universe that's more complex, more dynamic, and more surprising than the models predicted. That's not a failure, that's progress. Science doesn't advance by confirming what we already know. It advances by finding things that don't fit, and then doing the hard work of figuring out why they don't fit. The anomalies Webb has found, the structures that break the cosmological principle, the galaxies that assembled too fast, the expansion rate that won't settle down, these are gifts, inconvenient gifts, sure, uncomfortable gifts that force cosmologists to question assumptions they'd rather not question, but gifts nonetheless, because they're pointing the way forward, they're telling us where the model needs work. They're showing us the edge of our understanding and inviting us to push past it. The next decade is going to be fascinating. Webb will keep observing. Euclid will map the distribution of galaxies. Roman will survey supernovae. The extremely large telescope and its siblings will come online and start probing the universe with unprecedented clarity. And with each new observation, with each new data set, the picture will come into sharper focus. Maybe the tensions will resolve, maybe they'll deepen, maybe entirely new anomalies will appear that no one has anticipated. But whatever happens, cosmology is moving, the field is alive. The questions are hard, and the answers, when they come, are going to reshape our understanding of the universe we live in. We are living through one of those rare moments in science where the ground is shifting, where the old certainties are being questioned and the new framework hasn't emerged yet. It's uncomfortable, it's messy, and it's exactly where the most important work gets done. The universe has handed cosmology a series of puzzles that the standard model can't quite solve. The big ring that shouldn't exist, the giant arc that's too large, the galaxies that formed too fast, the expansion rate that won't agree with itself. And the only way forward is to stop patching the cracks and start asking whether the foundation needs rebuilding, not from scratch, but with new materials, new tools. A deeper understanding of how gravity, matter, energy, and space itself behave at the scales where we're only now beginning to look closely. The cosmic playbook is being rewritten. Not all at once, not by a single breakthrough or a single telescope, but piece by piece, observation by observation, anomaly by anomaly. And when the new version is finished, whenever that is, however long it takes, it's going to describe a universe that's stranger and more wondrous than the one we thought we knew. That's the promise, that's the challenge, and that's the future of cosmology. So where does that leave us? Standing in front of a universe that refuses to cooperate. A universe that built galaxies faster than it should have, organized matter into structures larger than the rules allow, and is currently flying apart at a speed no one can agree on. A universe that, after a century of careful observation and elegant mathematics, has decided to stop making sense in precisely the ways we expected it to. The Big Ring is still there, 1.3 billion light-years across, sitting exactly where the cosmological principle says nothing that organized should exist. The giant arc is still there, 3 times larger than the theoretical maximum, stretching across a region of space that should have smoothed out billions of years ago. Webb's impossible galaxies are still there, fully formed and shining brightly in an infant cosmos that should have been stumbling through its first generation of stars. The Hubble constant is still giving 2 different answers, and the gap between them is not closing. These are not problems that are going away. They are not measurement errors waiting to be corrected. They are the universe telling us, loudly and consistently, that the story we've been telling about how it works is missing chapters. And maybe that's the point. Maybe the lesson here isn't that cosmology has failed, but that the universe is deeper and stranger than any model built by humans could fully capture. We mapped the cosmos with 6 parameters and got remarkable agreement for decades. Now the edges are fraying, and instead of panic, what we're seeing is science doing exactly what it's supposed to do. Adjusting, questioning, rebuilding, not because the old framework was wrong, but because the new data demands better. The universe doesn't owe us simplicity. It doesn't owe us answers that fit neatly into equations we already understand. It just is what it is. And our job, the only job that matters, is to keep looking, keep measuring, keep asking why the thing we just found refuses to behave. Because that refusal, that friction,